Deep in a dark museum archive, under humming lights and drifting dust, a single massive bone rests on a metal shelf. No skull, no skeleton, just one colossal fragment from an ancient world. Its surface is cracked, its edges worn. Yet from this lonely relic, an entire dinosaur species has been named. Not a full skeleton laid out in pristine glory. Not even a complete limb. Sometimes it is just one vertebra, a chunk of hip, a single limb bone thicker than your torso. And from that one piece of evidence, we speak of giants as if we know them. We read confident names in textbooks. We see towering silhouettes in documentaries. We repeat claims about the biggest creatures to ever walk the earth, as though they were carved in stone. But what if those claims rest on only one bone? What if that bone is distorted, weathered, or incomplete? In paleontology, there is a rule at the heart of every species: the holotype. One defining specimen that legally anchors a name. For some dinosaurs, that holotype is a beautiful, nearly complete skeleton. For others, it is a single, fragile fossil that could fit in your hands. This is where awe collides with uncertainty. Here's the paradox we face. We live in an era of high-resolution scans, digital 3D models, and powerful computers. Yet some of our most dramatic dinosaur records trace back to scraps discovered more than a century ago. We talk about record-breaking sauropods and exotic predators, even when the reality is a lone vertebra drawn in an old notebook, or a bone that has since gone missing. How can we name a whole species from just one fragment? And what happens to our picture of evolution when that fragment is questioned? Join us as we step back hundreds of millions of years and also dive into CT scanners and dusty archives to follow the trail of these one-bone giants. We will meet names that once shook the dinosaur world. Ultrasauros, assembled from enormous bones that later turned out to belong to other known species. Bruhathkaiosaurus, rumored to be a titan beyond all others, described from fossils that may have crumbled away in a monsoon. Amphicoelius fragilimus, recently renamed Mara apunisaurus, a sauropod so vast it could rival skyscrapers, known only from a vertebra described in the 1870s and then lost. These fragmentary fossils do more than spark headlines. They set the stage for taxonomic chaos. One misidentified bone can create a new species that later collapses into a synonym, a duplicate of something we already knew, or is branded a dubious name and quietly fades from the scientific record. Yet museum displays, world record lists, and our mental image of a world of scale we can barely imagine still lean on these ghosts of data. The stakes are both scientific and deeply human. Researchers spend decades chasing the sites where these bones were found, hoping for just one more piece. Artists and educators build entire bodies around a single fossil clue. And you are left wondering, how much of what we think we know about the largest dinosaurs is real, and how much is mirage? Before we answer, consider this. One of the most famous, largest dinosaurs ever is based on a bone that no one alive today has ever seen in person. Only an old sketch remains. What does that do to our giants? That single lost bone takes us to the quiet legal machinery behind every dinosaur name. Hidden beneath the colossal reconstructions and dramatic artwork is a simple rule. Each species, no matter how massive or mysterious, is tied to one physical object. That object is called the type specimen. In biological nomenclature, the type specimen, or holotype, is the name-bearing reference for a species. It might be a full skeleton. It might be a partial skeleton. In some cases, it is just one vertebra, one tooth, or a shattered fragment of hip. Under the International Code of Zoological Nomenclature, that piece of fossilized bone becomes the official anchor for the name, the standard to which all later discoveries must be compared. How does a random bone become that anchor? A paleontologist studies the fossil in detail, measuring it, describing its shape, and diagnosing unique features, called autapomorphies, that seem to separate it from all known species. They compare it with other bones from the same era and region, and with skeletons of related dinosaurs from around the ancient world. If the fossil appears distinct, they write a formal description, submit it to a peer-reviewed journal, and, crucially, designate that specimen as the holotype, housed in a recognized museum or collection. In theory, this process is careful and conservative. In practice, especially in the 19th and early 20th centuries, the reality was more chaotic. During the Great Age of Exploration and the infamous Bone Wars, scientists were often working with very few known dinosaurs for comparison. New fossil beds promised a world of scale we can barely imagine, and the pressure to claim the biggest creatures to ever walk the earth was intense. Naming a new species from a single bone was not only allowed, it was often celebrated. Think of the holotype as a birth certificate. It does not tell you everything about a person's life, but it is the legal document that fixes their identity. In the same way, a lone vertebra or toe bone can serve as the birth certificate of a dinosaur species. No matter how incomplete it is, every future fossil that might belong to that species must ultimately be checked against that original piece of evidence. Around the holotype, other terms orbit. Additional specimens described in the same paper can be named paratypes, supporting characters that help flesh out the anatomy of the species but do not carry the legal weight of the name. If the holotype is lost or destroyed, a new standard can be chosen, called a neotype, to rescue the name from vanishing. And underlying all of this is a critical judgment. Is the fossil diagnostic, with features sharp enough to distinguish it, or non-diagnostic, so plain that it could belong to many similar dinosaurs? Here is where the tension builds. Naming a species from a single bone is sometimes the only option in a fragmentary fossil record. Yet it can also plant a time bomb in the literature. What happens if that bone turns out to be distorted, or belongs to a juvenile, or is simply too ordinary to tell apart from its neighbors? In the next section, we will see how such fragile names can reshape, and sometimes shatter, our picture of dinosaur diversity and size. Out on a windswept stretch of badlands, the illusion of perfect skeletons falls apart. Scattered across the dust are single vertebrae, broken ribs, the rounded end of a femur bleaching in the sun. Before museums, before mounting frames of steel, this is what the ancient world really leaves us. Fragments. Complete dinosaurs with every bone in place are the rare exception. Most of the time, we meet the biggest creatures to ever walk the earth, one lonely piece at a time. To understand why, we have to follow a carcass through the taphonomic gauntlet. A giant dies, and scavengers arrive first, tearing flesh, dragging limbs, scattering bones. Floods and rivers roll those bones downstream, grinding them, separating heavy limb bones from delicate skull pieces. Some parts sink and are buried quickly in mud. Others lie exposed, weathering, cracking, and eventually dissolving away. Millions of years later, erosion cuts back through those ancient sediments and frees whatever survived. Often, it is not a skeleton. It is a single vertebra, a partial limb, a chunk of hip, lying far from where the animal fell. From that one bone, paleontologists still try to read a life. A massive thigh bone can hint at overall size and weight, letting us estimate whether we are dealing with an elephant-sized animal or a true titan rivaling Argentinosaurus. The shape of a vertebra can reveal whether it came from a long-necked sauropod or a meat-eating theropod. The angle of a joint surface can whisper clues about posture and locomotion. Sometimes, a bone bears distinctive ridges or hollows, a unique combination of features that seems to set the stage for naming a new species. Yet a single bone is also a wall we cannot see past. It cannot reliably tell us the full proportions of the body, the exact mass, or the detailed shape of the skull that bit, breathed, and sensed its world. It says nothing clear about skin coverings, coloration, social behavior, or the fine branches of the evolutionary tree within a clade. How much would you truly know about a person if all you had was one femur? Imagine trying to reconstruct an entire human from just that thigh bone. You might estimate height, guess at sex, perhaps infer whether they were robust or slender. But could you picture their face, their hair, their clothing, their daily life? In the same way, we risk projecting whole ways of living onto giants we know only from a single vertebra. This is why some bones are prized as diagnostic, while others remain stubbornly anonymous. A specialized claw or a unique skull element can carry a signature combination of traits. A generic mid-back vertebra, by contrast, can look frustratingly similar across several related species. Yet history shows that even these ambiguous bones have inspired sensational claims. During the great rush to understand dinosaur evolution, scientists sometimes stretched limited evidence into colossal narratives of size and diversity. Join us as we follow those narratives into controversy. In the next section, we will meet one contender for largest dinosaur ever, known from a vertebra so fragile it crumbled away, leaving behind only drawings, measurements, and a mystery that still shapes how we imagine a world of scale we can barely imagine. We cut from fragile sketches and lost bones to something far more solid, towering gallery halls filled with life-sized dinosaurs. Necks sweep overhead like living cranes of bone and muscle. In glossy documentaries, CGI sauropods move through digital forests, their backs higher than houses, their footsteps making the ancient ground tremble. Again and again, the narration returns to one irresistible question. Which was the biggest dinosaur ever? Before humans, before cities, before history itself, the Earth belonged to giants. Not just big animals, but true titans, the biggest creatures to ever walk the Earth. Our books, our online lists, our museum posters rank them like heavyweight champions, each new contender edging out the last by a few meters of length or a few tons of mass. Yet hidden behind those confident numbers is a quieter, more uncomfortable reality. Many of the names that dominate record books are not based on near-complete skeletons like Argentinosaurus or Patagotitan. They are based on fragments, sometimes a handful of bones, sometimes just one. A single vertebra, one massive limb bone, a partial hip. From these slivers, we try to reconstruct entire bodies, entire lives, and entire ecosystems. On screen, though, the uncertainty often disappears. Museum halls display full reconstructions where only a few bones are original. Documentaries glide past the missing pieces, presenting sleek, fully fleshed giants as if every rib and toe bone had been dug from the rock. How often do we stop and ask, how much of this animal actually exists in the fossil record, and how much has been carefully inferred? To bridge the gap, paleontologists use scaling relationships. A single oversized vertebra is compared to better-known relatives. Its proportions are fed into equations that link bone size to overall body length and mass. The method is powerful, but sensitive. Change the assumed body shape, neck length, or density of soft tissues, and the result can shift by tens of tons. One assumption here, one adjustment there, and an already massive sauropod becomes almost unimaginably colossal. Some of the most dramatic examples have become familiar names. Ultrasauros, once hailed as a supersauropod towering over its Jurassic neighbors. Bryonchiosaurus from India, initially reported as a creature so heavy it seemed to strain the limits of biology. Amphicalius fragilis, now often called Mara apunisaurus, known from a vertebra so enormous that, if the original measurements are correct, it would dwarf nearly every other land animal in history. These names echo through dinosaur pop culture. They shape children's books, viral videos, and mental images of the Mesozoic era, sometimes far out of proportion to the actual evidence behind them. They set the stage for a world of scale we can barely imagine, but they may also distort it. Here is the tension we must confront. our awe is genuine. The Mesozoic really did produce creatures of staggering size, yet some of the most extreme record holders may be mirages, born from fragmentary fossils and optimistic interpretations. In the next section, join us as we dissect these famous giants one by one, asking a simple, unsettling question. Did they truly exist as described? Or are they artifacts of scientific overreach and the limits of the rocks themselves? Our first suspect is a giant that, for a time, seemed to rewrite the record books. Not through a complete skeleton, but through a single colossal bone. When we meet Ultrasauros, we step into a world of scale we can barely imagine, and into the heart of the problem with naming the biggest creatures to ever walk the earth from fragments. In the 1970s and 1980s, excavations in the Morrison Formation of North America uncovered scattered bones from massive sauropods. Among them was a scapulocoracoid, the fused shoulder girdle bone, so huge that it appeared to dwarf those of familiar Jurassic giants like Brachiosaurus. Before humans, before cities, before history itself, this landscape was ruled by long-necked herbivores, but this bone seemed to hint at something beyond even that Jurassic norm. At first, many researchers treated the giant shoulder and several other large bones from the same quarry as parts of one animal. Not just a big sauropod, but a supersaur. Early size estimates projected a creature longer and heavier than any known brachiosaur, a dinosaur that might tower over already enormous highbrowsers and set the stage for breathless headlines. Popular books and documentaries seized on the name Ultrasaurus, later standardized as Ultrasauros mackintoshi, presenting it as a pinnacle of dinosaur evolution, a symbol of how far gigantism could go. Yet names and excitement are one thing. Anatomy is another. As the initial rush faded, paleontologists returned to the bones with more careful comparative methods, matching curves, muscle scars, and joint surfaces against better-known skeletons. Piece by piece, the illusion began to unravel. The gigantic scapulocoracoid turned out to fit comfortably within the range of a very large Brachiosaurus-like animal, while other bones from the site clearly belonged to different sauropods, including forms closer to Diplodocus or Supersaurus. What had looked like a single individual was actually a chimera, a mixed assemblage from multiple giants jumbled in an ancient bone bed. In such crowded deposits, erosion, scavengers, and water currents easily scatter and mingle skeletons, making it dangerously simple to merge several animals into one imagined colossus. When a name is built on that kind of mixture, how stable can it really be? The taxonomic verdict was decisive. Ultrasauros mackintoshi was reinterpreted as a junior synonym or misapplied label, its keybones reassigned to already named genera. In the technical literature, Ultrasauros effectively vanished as a valid dinosaur. Yet in older books, museum posters, and online lists, the supersaur still lingers, a ghost giant echoing an outdated moment in our understanding of Earth's ancient world. Ultrasauros warns us that even spectacular, well-publicized giants can dissolve under scrutiny. If one of the supposed largest dinosaurs ever can disappear once we look closely at a single shoulder bone, what does that mean for other record breakers known from even less? Join us as we turn to creatures based on one vertebra, one sketch, or one lost fossil, and ask an even more unsettling question. What happens when the bone itself is gone? When the bone itself is gone, we are left with shadows. And few shadows in dinosaur science are as large or as controversial as Bryhathkaiosaurus. Discovered in southern India in the 1980s, this animal was given a name that roughly translates to huge-bodied lizard. Even in an ancient world ruled by giants, that is an audacious title. Early reports hinted that it might rival or even surpass the biggest creatures to ever walk the earth, titanosaurs like Argentinosaurus and Patagotitan. Were we looking at a new champion of size, or at a mirage born from fragmentary stone? The original fossils were not a majestic, complete skeleton. They were scattered pieces, parts of massive limb bones, fragments of the hip, and portions of vertebrae eroding from monsoon-battered sediments. The rocks of that region are heavily weathered, split by seasonal rains, and the bones were already in poor condition when they were collected. Rough field measurements suggested astonishing dimensions, especially for a leg bone that, if interpreted as a femur, implied a truly colossal sauropod. From the beginning, though, Bruhathkaiosaurus sat in a storm of doubt. Some paleontologists questioned whether these remains were even from a dinosaur. Could they belong instead to a huge crocodile-like reptile or some other Mesozoic creature? Others argued that the fossils were simply too distorted, too incomplete, and too poorly documented to classify with confidence. When we set the stage for records based on fragments, how much uncertainty are we willing to accept? The preservation story only deepens the mystery. Reports indicate that the bones were heavily weathered, partly encased in very hard rock and difficult to prepare. Over time, they may have deteriorated, broken apart, or even been discarded. Today, researchers trying to study Bruhathkaiosaurus must rely on old photographs, brief descriptions, and a handful of published measurements. There is no specimen in a museum drawer waiting for CT scanning, no skeleton to turn into a 3D model. The result is a dizzying range of size estimates. Some reconstructions treat Bruhathkaiosaurus as simply a large but not record-breaking titanosaur. Others scale the fragmentary bones in ways that produce staggering numbers, suggesting an animal longer than 35 meters and heavier than any known land vertebrate. Which version is real? With so few pieces, tiny changes in interpretation ripple outward into wildly different visions of this ancient giant. Without the original fossils available for modern reanalysis, Bruhathkaiosaurus remains more rumor than resolved reality. Join us as we consider what this means. An animal that might redefine the upper limits of dinosaur size, yet cannot be tested by today's tools of comparative anatomy and digital modeling. Its story shows how tantalizing but poorly documented remains can fuel headlines, online debates, and dramatic artwork, while offering very limited hard data on dinosaur evolution and true size limits. In the end, Bruhathkaiosaurus could be a genuine supersauropod, a misidentified reptile, or something in between. Until new, better preserved bones emerge from the rocks of India, its true nature will stay just out of reach. A reminder that in this era of discovery, we still live with a world of scale we can barely imagine, and Bruhathkaiosaurus is not alone in this uncertainty. Next, we turn to other giants known from a single bone or a single sketch and ask how much of our record book might rest on vanishing evidence. If Bruhathkaiosaurus is a whisper from the past, Amphicoelius fragilis is a ghost story. Not just a missing giant, but a colossal question mark that still haunts our picture of the biggest creatures to ever walk the earth. To meet it, we step back hundreds of millions of years in our minds to the late Jurassic Morrison Formation of Western North America. This was an ancient world of towering conifers, fern plains, and herds of sauropods moving like living hills across the floodplains. In the 1870s, amid the frenzy of the Bone Wars, paleontologist Edward Drinker Cope reported something extraordinary from this period. A single dorsal vertebra of a sauropod he named Amphicoelius fragilis. Cope's description reads almost like science fiction. The preserved portion of the vertebra, he wrote, stood over 2 meters tall, with the missing parts pushing its original height even further. When you scale that up using better-known sauropods from the same formation, you arrive at an animal that could exceed 50 meters in length, with a mass far beyond Argentinosaurus or Patagotitan. Not just big animals, but true titans. A world of scale we can barely imagine, inferred from one shattered backbone. Yet the name fragilis was tragically accurate. Even in Cope's time, the bone was crumbling, its internal structure so delicate that transport and storage were a constant risk. Sometime after his initial study, the vertebra was reportedly damaged and ultimately lost. Today, all that remains is Cope's written description and a single sketch. No plaster cast, no photographs, no specimen drawer to reopen and re-examine. For decades, Amphicoelius fragilimus occupied a strange space in paleontology. Popular books and documentaries cited it as the largest dinosaur ever, while many scientists treated it with deep caution. How far can we trust a size estimate that rests entirely on one 19th century drawing? Was this truly a record-breaking sauropod, or a measurement error frozen in print? Modern reevaluations have only sharpened the debate. Some researchers have suggested that Cope's measurements may include transcription mistakes, perhaps a misplaced digit that inflated the scale of the vertebra. Others argue that, if those numbers are accurate, the bone could represent a truly gigantic diplodocoid, related to slender giants like Diplodocus, but on an almost unthinkable scale. More recently, a detailed reanalysis proposed that this animal was not a classic Amphicoelius at all, but a different lineage, a rebecasaurid sauropod. Under this interpretation, the species was renamed Mara apunisaurus fragilimus, and its anatomy was reconstructed by comparing Cope's notes with better-known relatives from South America and Africa. Join us as we watch paleontologists try to resurrect a vanished giant from a handful of ink lines. And yet, the core problem never changes. Without the actual bone, Amphicoelius Mara apunisaurus remains a ghost taxon, a name anchored to evidence no one can independently verify. It is a powerful reminder that claims about extreme dinosaur size are only as strong as the fossils and the curation behind them. What happens then when not just one, but dozens of such fragmentary, uncertain species are scattered across the dinosaur family tree? Those ghostly giants are not alone. Once we step back hundreds of millions of years and look across the entire dinosaur family tree, we find that Amphicoelius is just one specter in a crowded hall of phantoms. It is easy to focus on sauropods because the biggest creatures to ever walk the earth make headlines. But the habit of naming a whole species from a single bone, or even a single tooth, runs through nearly every major dinosaur group. Theropods, the predatory line that eventually gave rise to birds. Ornithopods, the beaked plant eaters that would later include duckbills. Ceratopsians, the horned dinosaurs of the late Cretaceous. Each of these clades carries its own share of one-bone enigmas. Join us as we imagine a 19th century quarry in Europe or North America. A collector uncovers an isolated claw, a lone vertebra, or a distinctive tooth from a Jurassic or Cretaceous layer. At the time, that fragment looks unusual. The curve of the claw seems sharper, the ridges on the tooth slightly different, the proportions of the vertebra unlike anything described before. In an era when the fossil record was still being charted, those subtle differences often felt like enough to set the stage for a brand new genus and species. Some of the most notorious examples are the so-called tooth taxa. A single serrated tooth from a meat eater might be christened as an early theropod species, even though similar teeth can occur in several closely related predators. Likewise, a worn, leaf-shaped tooth from a small ornithischian might be given its own name, despite the fact that many beaked plant eaters share nearly identical dental batteries. When the defining feature of a dinosaur is just one tooth, how can we be sure which animal it truly belonged to? In fossil-rich formations with long collecting histories, this practice left a dense trail of names. The Morrison Formation in North America, the Wealden Rocks of England, and many Cretaceous beds in Asia and South America all contain species based on fragmentary, non-diagnostic material. Modern paleontologists often regard these as nomina dubia, dubious names that cannot be tied confidently to a unique, diagnosable animal. Over time, as more complete skeletons emerged from the same rocks, many of these one-bone dinosaurs were quietly abandoned or folded into better-known species. a tooth once thought to represent a separate predator might be reinterpreted as simply another individual of an already named giant. A stray vertebra could be reassigned to a familiar herbivore. Yet the original names linger. They survive in older books, in museum drawers and labels, and in online lists that seem to promise a world of scale we can barely imagine. This is more than an archival inconvenience. Inflated species counts distort our picture of dinosaur diversity, scramble evolutionary family trees, and even mislead us about how many predators and prey shared an ancient ecosystem at any one time. So if the literature is cluttered with ghosts, how do paleontologists decide which names to keep, which to retire, and how to clean more than a century of taxonomic debris from the fossil record? To untangle that debris, we first have to face an uncomfortable truth. Dinosaur taxonomy has a long history of chaos. Not just a few confusing names, but entire genera that became catch-all bins for whatever fragmentary bones early collectors pulled from the rock. In this ancient paperwork trail, one-bone species are often the worst offenders. In the 19th century, pioneers worked with limited material and an overwhelming sense of discovery. When a tooth, a vertebra, or a chunk of jaw looked even vaguely similar to something already named, it often went into the same category. These became wastebasket taxa, genera or species that served as dumping grounds for miscellaneous, poorly preserved, or hard-to-classify fossils. Over decades, they swelled into taxonomic junk drawers that blurred the real outlines of dinosaur evolution. Megalosaurus is a classic example. Originally described from a few bones in England, it quickly turned into a label for almost any large theropod scrap from the Jurassic of Europe and beyond. Teeth, isolated limb bones, partial jaws, many of them probably from different predators, were all filed under the same banner. Iguanodon followed a similar path. Before more complete skeletons were found, scattered teeth and bones from multiple ornithopods were lumped together as a single, vaguely defined, giant herbivore. Out of this confusion emerges another crucial term, nomen dubium, literally a doubtful name. A nomen dubium is a scientific name based on material so incomplete or non-diagnostic that we cannot reliably distinguish it from other taxa. The holotype, that single defining specimen, sometimes only one bone, lacks clear, unique features. As new, better skeletons appear, the old name becomes effectively unusable for precise science. One-bone species are especially vulnerable. A ridge on a femur, a groove on a vertebra, a slightly unusual tooth may look distinctive when we know very little. But as we discover more complete giants from the same period and region, those supposed hallmarks often fall comfortably within normal variation of already named species. What once seemed like a window into a new dinosaur becomes a blurry reflection of one we already know. Then there are synonyms, different names that, after careful comparison, turn out to refer to the same animal. Often, an early fragmentary species is described first, and later, a more complete skeleton from the same strata receives a new name. Only when someone painstakingly re-examines the old bone and the new skeleton side by side do we realize they belong to the same creature. Which name should stand? Which becomes a historical footnote? The practical consequences are immense. Wastebasket taxa and nomina dubia inflate species counts, make the literature difficult to navigate, and hide true patterns of diversity behind layers of redundant or meaningless labels. The biggest creatures to ever walk the earth sometimes appear under 2, 3, or even more different names in different papers. How do we trace real changes through time when the very labels on the fossils keep shifting? Cleaning this up requires slow, meticulous taxonomic revision. Paleontologists return to dusty museum drawers, remeasure old-type specimens, and compare them with new finds using modern imaging and rigorous anatomical criteria. They publish formal decisions to declare names dubious, to synonymize species, or to restrict old names to better defined material. Join us as we step back hundreds of millions of years in the scientific record itself, watching how each ruling reshapes our view of the Mesozoic world. This work does more than tidy a checklist. It helps set the stage for answering the grand questions. How quickly did different lineages rise and fall? When did certain body plans appear? And how often did true giants evolve? Yet the one-bone legacy makes that task slow, contentious, and sometimes impossible. In the next section, we will see how new technologies and fresh discoveries can occasionally rescue these ghostly names, and just as often sweep them away entirely, forcing us to redraw the map of dinosaur diversity once again. Yet even when new technologies arrive, a single bone carries another danger. It is not only incomplete, it is exposed to misinterpretation at almost every level, especially when it is found alone in a cliff face or tangled in a complex fossil bed filled with the remains of many different creatures. Before we can measure a giant, we must be sure we know what that lonely fragment actually is. When we step back hundreds of millions of years in our minds and imagine these bones settling into river mud or floodplains, we see how confusion begins. A worn limb shaft from a dinosaur can look remarkably like the limb of a giant crocodile relative or even a prehistoric mammal-like reptile. A single toe bone may be cataloged as a theropod claw when it truly belongs to a turtle. Even within dinosaurs, left and right limb bones can be reversed, forelimbs mistaken for hind limbs, and fragments of hip or shoulder girdle relabeled as parts of the tail. How many supposed one-bone species rest on such quiet early mistakes? History is filled with examples where fragments were placed in the wrong group and only later rescued. In the early days of dinosaur science, massive vertebrae and limb bones from sauropods were sometimes assigned to carnivorous theropods, inflating the size of the biggest predators to ever walk the earth. In other cases, robust theropod bones were folded into sauropod collections, assumed to belong to the same colossal plant eaters that shared the quarry. Only when more complete skeletons emerged from new sites did patterns become clear, and those stray bones were reclassified, sometimes stripping entire names from the record. Ontogeny, the changes that occur as an animal grows, adds another layer of uncertainty. Juvenile dinosaurs often have proportionally large heads, slender limbs, and bones that are not yet fully fused, with smoother surfaces and less dramatic muscle scars. An isolated juvenile thigh bone can look so unlike the adult form that, for decades, it may be described as a new species or even a new family. Later, when growth series are assembled from hatchling to adult, those supposed species vanish, revealed as mere life stages of a single lineage. Then there's the rock itself. Erosion can shear away ends of bones. Deformation can squeeze them like clay. And incomplete exposure can hide vital features in the cliff. A vertebra stretched by geological pressure may suggest a creature of impossible length. A broken ridge, misread as a unique crest or articulation, can be used to argue that a bone represents a completely new branch of evolution. In a world of scale we can barely imagine, even a few millimeters of missing surface can mislead. These misidentifications do not stay isolated. They ripple outward. A misclassified one-bone species can be fed into computer analyses of family trees, used to map the spread of dinosaurs across ancient continents, or included in charts that compare body size through the Mesozoic era. Each time, the error subtly bends the story we tell about diversity, geography, and the rise of giants. Today, modern comparative collections and digital databases set the stage for more careful work. Paleontologists can match an isolated bone against thousands of cataloged specimens, rotate 3D scans, and test identifications with unprecedented precision. Join us as we look ahead, because as these tools refine our view, some famous one-bone dinosaurs will shrink, vanish, or migrate to new branches of the dinosaur family tree, reshaping our picture of the Mesozoic world in ways we are only beginning to grasp. Those digital tools are not just fancy ways to look at old bones. They are our best chance to pull new secrets out of fossils that seemed, for more than a century, to have said all they could say. When a whole species rests on a single bone, every hidden detail inside that fragment matters. This is where high-resolution CT scanning transforms the game. Instead of slicing a priceless vertebra or femur, we can see through it, layer by layer, without leaving a scratch. Join us as we move from the frustration of misidentification to the quiet power of imaging, watching ancient structures appear on screen. Airspaces like honeycomb, dense load-bearing struts, even growth rings frozen since an era before mammals rose to dominance. Those inner patterns are not just pretty pictures. Air-filled cavities can signal that a bone belonged to a sauropod with bird-like lungs rather than a more solid-boned reptile. Variations in bone density trace where muscles anchored and forces traveled, hinting at how a limb moved or how a colossal tail balanced the front of the body. In some specimens, CT slices reveal lines a bit like tree rings, marking growth stages and suggesting whether a bone came from a juvenile, a subadult, or a fully grown giant. From these scans, researchers build precise 3D digital models. Sometimes they use surface photogrammetry, stitching together hundreds of overlapping photographs to capture every ridge and crack. Once the bone lives in the computer, they can virtually straighten fossils crushed by millions of years of sediment, mirror missing left or right elements, and compare shapes with statistics rather than guesswork. This is geometric morphometrics in action, aligning key landmarks, measuring subtle curves, and testing whether an isolated bone truly matches a known species or belongs to something new. With a 3D model, a single bone no longer floats in isolation. It can be digitally articulated into skeletons of close relatives, rotated and resized to test different body plans. Could this giant femur really support a 50-ton sauropod? Or do the joint surfaces fit a more modest animal? By scaling against better-known skeletons, scientists refine size estimates and reject reconstructions that would have produced impossible proportions in the biggest creatures to ever walk the Earth. In recent years, CT and modeling have clarified fragmentary finds from places like South America and Asia, where isolated vertebrae once hinted at mysterious giants. Some bones, once thought to represent record breakers, turned out, after internal scans and shape analysis, to belong to more ordinary titanosaurs, or even to different reptile groups entirely. Others gained new importance when airspace patterns and growth markers tied them securely to particular dinosaur lineages, rescuing them from the limbo of dubious names. Yet there are hard limits. No scan can conjure a missing skull. No model can reveal feathers, skin, or exact posture when only a single hip bone survives. These techniques magnify the information locked in each fragment, but they cannot erase the gaps left by extinction, erosion, and chance. What they can do is share that information with the world. High-resolution scans and finished 3D models can be sent across continents, letting independent teams test the same one-bone holotypes without risking damage to the originals. In a sense, every fragile vertebra can now exist in many laboratories at once, its measurements and internal structures checked, rechecked, and fed into new analyses. Together, CT imaging and digital modeling set the stage for a broader toolkit that still must bow to the fragmentary fossil record. As we step back hundreds of millions of years in our imagination, we carry these modern instruments with us, knowing they will sharpen our view of ancient giants, but never fully replace the simple, irreplaceable power of finding more bones in the ground. And that search, as we will see next, reshapes not just individual species, but our entire picture of dinosaur evolution and diversity across a world of scale we can barely imagine. To turn those scattered clues into real animals, we rely on something deceptively simple: looking closely at bones, not just seeing them, but reading them. Comparative anatomy is the traditional backbone of paleontology, the craft of asking, from every curve and ridge, what kind of creature this fragment once helped to move across ancient Earth. When we study a single vertebra or femur, we are not seeing it in isolation. We are silently comparing it to hundreds of others, The shape of the joint surfaces, the angle of a ridge, the position of a muscle scar, the way the bone wall thins or thickens along its length. All of these act like a barcode. Join us as we follow that code through time, matching lonely fossils to their families among the biggest creatures to ever walk the earth. Over generations, specialists build mental and digital libraries of variation. They learn the usual range of sauropod dorsal vertebrae, from blocky Camarasaurus to elongated Diplodocus, and the many forms of theropod femora, from deep, powerful meat eaters to more lightly built predators. They factor in growth, knowing that a juvenile's bone will differ from that of an adult, yet still belong to the same colossal lineage. This is why old one-bone species do not stay frozen in the moment they were named. As new, more complete skeletons are described, paleontologists return to those original holotype bones and ask, are these features truly unique or simply part of normal variation? Again and again, traits once thought to define a new species turn out to be widespread or even caused by damage and distortion. Consider a fragmentary sauropod named from a single dorsal vertebra during the early rush to catalog giants. Decades later, with extensive skeletons of related dinosaurs in hand, researchers noticed that the proportions of the centrum, the pattern of laminae, the thin bony struts, and the arrangement of air spaces matched those of an already known genus. The supposed new titan was quietly folded into that familiar name, its species declared a junior synonym, and the taxonomic record became a little cleaner. Comparative anatomy is not merely about visual resemblance, it is also about measurements and numbers. The ratio of height to width in a vertebra, the angle between processes, the statistical spread of shapes within a group. Where does our orphan bone fall on those graphs? Deep inside the cloud of known variation, or far beyond its edge? To answer that, researchers turn to reference collections, to drawers lined with labeled bones from multiple individuals and species. Here they can place an isolated vertebra beside a whole series from neck to tail, or a lone femur among dozens of known forms, and let direct comparison set the stage for careful judgment. There is, inevitably, subjectivity. Two experts may initially disagree about whether a ridge is distinctive enough to uphold a species. Yet, as more fossils emerge, scans accumulate, and measurements are shared, consensus usually forms. In the end, comparative anatomy is one of the main tools we use to decide whether a one-bone name represents a valid species, belongs within an existing dinosaur, or must sink into the limbo of dubious names. And that decision will shape how we reconstruct dinosaur evolution in a world of scale we can barely imagine. But bones do not exist in isolation. They are locked into layers of rock, and those layers tell a parallel story. If comparative anatomy asks, what does this bone look like? Stratigraphy asks, where and when in Earth's history did it come from? Together they set the stage for how confidently we can name a species from a single fragment. Stratigraphy is simply the study of rock layers and their order. Before humans, before cities, before history itself, sediments were piling up in rivers, lakes, and seas, building a stacked archive of the ancient world. When we step back hundreds of millions of years and look at that archive, each layer has an age, a chemistry, and an environment written into it. If we know exactly which layer a lonely bone came from, we already know far more than its shape alone can tell us. This is why a single bone from a well-studied formation, like the Jurassic Morrison Formation or the late Cretaceous Hell Creek, is so powerful. In those rocks, the age is tightly constrained and the dinosaur fauna is relatively well mapped. An isolated femur from Morrison sandstones can be compared not only to the anatomy of known sauropods, but also to the time slice and ecosystem those giants lived in. Does it match the colossal diplodocids and brachiosaurs we already know from that horizon? Or does it fall outside their known variation? Modern fieldwork treats context as sacred. Join us as we follow a bone from discovery to documentation. GPS coordinates are logged, detailed stratigraphic columns are drawn, and the surrounding sediments are described grain by grain. With that information, paleontologists can say, for example, that a fragmentary vertebra comes from a thin mudstone bed that elsewhere yields Triceratops and Tyrannosaur remains, but no hadrosaurs. Instantly, some identifications become more probable, others far less likely. Sometimes, stratigraphy flatly contradicts an exciting claim. A bone might be proposed as belonging to a particular dinosaur group, only for geologists to show that the rock is millions of years older than that group's first appearance, or long after its extinction. In several cases, supposed Jurassic hadrosaur bones or Triassic ceratopsians have been reinterpreted once their true stratigraphic positions were recognized. The rock record quietly ruled them out. The environment of deposition adds another filter. River floodplains tend to preserve the remains of large terrestrial herbivores and the predators that hunted them. Coastal swamps may be rich in duck-billed dinosaurs and crocodile relatives. Desert dune fields might favor small, lightly built animals that died near rare oases. When a lone bone emerges from a channel sandstone packed with giant sauropod tracks, it is far more likely to represent one of the biggest creatures to ever walk the earth than a small arboreal species we have never seen there before. Is that a guarantee? No. But it is powerful probabilistic reasoning. Many classic one-bone or few-bone species, named in the 19th and early 20th centuries, lack this level of context. Localities are vague, stratigraphic levels are uncertain, and original field notes are sometimes lost. Without that framework, it becomes much harder to test whether a fragment truly stands apart from known species, or whether it simply overlaps them in time and space. Today, paleontologists work hard to avoid repeating those mistakes. Every new bone is tied tightly to its rock record, so that even a single vertebra can be evaluated within a precise slice of time, place, and environment. In this way, the rock around the bone can support or undermine the case for a distinct species, and when the fossil itself is fragmentary, that context may be the deciding line between a meaningful name and yet another dubious ghost in our picture of dinosaur evolution. As we move deeper into how these decisions reshape size records and diversity counts, we begin to see just how fragile our image of dinosaur gigantism can be when it rests on one imperfect clue in stone. But how do we test where that imperfect clue belongs? How do we decide which branch of the dinosaur family tree a single, silent bone is whispering from? To answer that, we step into the world of phylogenetic analysis, often called cladistics. Here, paleontologists do not just line fossils up from small to large or ancient to recent. Instead, they code dozens, sometimes hundreds, of anatomical characters into a data matrix and let computer algorithms search for the most economical pattern of shared features. The result is a branching tree of descent, a hypothesis of evolution that tries to show which species are close relatives and which split apart earlier in deep time. To include any dinosaur in this kind of analysis, we must score it for that long list of characters: shape of the skull roof, arrangement of the teeth, curvature of the femur, details of vertebrae, hips, shoulders, and limbs. Each character becomes a series of numbers or states, shared or unique, that helps anchor a species among its relatives. When a skeleton is reasonably complete, the pattern that emerges can be powerful. It can set the stage for understanding where a new giant fits among the biggest creatures to ever walk the earth. But when we only have one bone, almost every character becomes a question mark. If the lone fossil is a tail vertebra, we know nothing of the skull, the ribs, the limbs, or the pelvis. In the matrix, that elegant grid of data, the row for our one-bone taxon, fills with blanks. The computer can still run, but the signal from that species is faint, overwhelmed by uncertainty. Where does such a ghostly presence belong on the tree? Often, the answer is that it floats. In one analysis, a fragmentary sauropod vertebra might cluster with titanosaurs. In another, it might slip toward diplodocids or collapse into an unresolved knot of branches called a polytomy. The Jurassic giant once labeled Amphicoelius fragilimus, later reinterpreted as Mara apunisaurus, has wandered through different positions in published trees, reflecting just how fragile its supposed relationships are when they rest on a lost, poorly documented vertebra. Faced with this instability, some researchers simply exclude extremely incomplete species from formal analyses, arguing that they add noise rather than clarity. Others include them cautiously to test whether any consistent placement appears when new data or new methods are applied. Both strategies reveal the same lesson. When we lack anatomical detail, our evolutionary stories slide and shift, and that has consequences. If a one-bone species cannot be reliably placed on the tree of life, it tells us almost nothing about when certain traits evolved, or how rapidly particular lineages diversified in a given era or region. Yet paradoxically, these same fragments still shape our sense of dinosaur diversity, biogeography, and even size records. Join us as we explore how such fragile clues can still reshape a world of scale we can barely imagine. Those fragile clues do more than fill museum drawers. They decide which giants wear the crown. For more than a century, the public story of dinosaur gigantism has orbited a single question: which was the biggest creature to ever walk the earth? Names like Ultrasaurus, Bruchithiasaurus, and Amphicoelius fragilimus, now often called Mara apunisaurus, rose to fame on exactly that promise. Yet each of these supposed champions rests on the thinnest of foundations. Ultrasaurus turned out to be a chimera, a mix of bones from different sauropods. Bruchithiasaurus is known from fragmentary material that may not even have been dinosaurian, now lost to weathering. Amphicoelius fragilimus was described from a single enormous vertebra that disintegrated, leaving only a sketch and a few measurements. When we step back hundreds of millions of years armed with only one bone and a ruler, how far can we really trust the record books? As paleontologists re-examine these fragments, many of the legendary giants are quietly downgraded, synonymized, or declared dubious. When that happens, the scoreboard of size changes. Ultrasaurus is removed from serious consideration. Bruchithiasaurus is treated with deep skepticism, and Mara apunisaurus is often bracketed as an intriguing but uncertain outlier. In their place, better documented titans rise. Argentinosaurus, known from substantial limb and hip bones; Patagotitan, represented by multiple individuals; Dreadnoughtus, with a remarkably complete skeleton for such a colossal animal. With these more reliable fossils, revised size estimates become more conservative. Early calculations for one-bone giants sometimes pushed well beyond 100 tons, extrapolating entire bodies from a single vertebra or limb. Modern scaling methods, grounded in broader comparative datasets and 3D volumetric models, usually pull those extremes back toward the known range of massive sauropods, on the order of 50 to perhaps 70 tons. Not small by any means, but less like mythical monsters, and more like the upper edge of a continuous, testable spectrum. These revisions reshape more than trivia about who holds the title. They change how we think about the limits of terrestrial life. If no dinosaur truly exceeded a certain mass, what does that say about bone strength, blood pressure, and the energy demands of keeping such a body alive? How productive must ancient ecosystems have been to sustain herds of animals heavier than modern whales on land? Each adjustment to a femur measurement or vertebra length feeds into models of biomechanics, metabolism, and even climate. When dubious giants are removed from analyses, broader evolutionary patterns shift as well. Apparent trends, such as an unbroken march toward ever larger sauropods through time, or the idea that particular continents, like Cretaceous South America, uniquely favored extreme body sizes, can weaken or even vanish once questionable data points are excluded. we begin to see not a simple escalation, but pulses of gigantism tied to changing environments, plant communities, and extinction events. Join us as we recognize that this is not a one-time correction, but an ongoing process. New fossils, new CT scans, and new statistical tools continually rewrite the list of record holders and refine our picture of size evolution across the Mesozoic era. In this way, science is self-correcting. One bone species may mislead us for a time, yet they also spark debate, drive fresh fieldwork, and set the stage for discoveries that bring us closer to a world of scale we can barely imagine. But if these fragmentary giants are so problematic, should we abandon naming species from single bones altogether? Or are there rare moments when one fossil really is enough to reveal something extraordinary? To see why that question matters, we need to meet the most famous one-bone giant of all. Not a complete skeleton, not even a limb, but a single colossal vertebra that has haunted dinosaur science for more than a century. We step back hundreds of millions of years in our minds, but the story itself begins in the late 19th century in the arid hills of western Colorado. During the Bone Wars, when rival paleontologists raced to outdo one another, Edward Drinker Cope's crews were combing Jurassic quarries for anything that might reveal the biggest creatures to ever walk the earth. In 1878, from the Morrison Formation near Canyon City, they shipped Cope a fragmentary yet extraordinary dorsal vertebra from a sauropod he named Amphicoelius fragilis. The bone was not just big, it was extreme. Cope's notes and measurements describe a neural arch towering more than 2 meters tall, with a total vertebra height possibly approaching 2.7 meters, dwarfing the already massive backbones of Diplodocus and Apatosaurus. If those numbers are accurate, scaling from better-known relatives suggests an animal stretching perhaps 40 to 60 meters in length, a giant that could rival or exceed Argentinosaurus and other record-holding titans. Are we looking at a true super sauropod, or an illusion born from a single fragile clue? Cope himself emphasized how delicate the fossil was. The bone was heavily weathered, riddled with internal cavities, and so brittle that even collecting it was a challenge. Housed in his collection in Philadelphia, it seems to have crumbled, been misplaced, or discarded during later moves and reorganizations. Today, no one can find the original vertebra. All that remains are a sketch, a scale bar, and a few lines of description in Cope's publications. That disappearance turns a real fossil into something closer to legend. Without the physical bone, we cannot remeasure it, test whether the proportions were misread, or check if erosion exaggerated its size. We cannot CT scan the interior, compare fine details of its articulations, or confirm exactly where in the backbone it belonged. For a type specimen, the reference that legally anchors a species name, this is a serious problem. It weakens Amphicoelius fragilis to the point where some scientists have argued it should be considered a dubious name. Yet the story did not end there. In the 21st century, paleontologist Kenneth Carpenter revisited Cope's data, comparing the sketch to better preserved diplodocid sauropods. He concluded that the giant belonged within this family, and in 2018, it was reassigned and renamed Marahapunisaurus fragilis, using a Native American term to reflect its North American heritage. Join us as we see how modern researchers use comparative anatomy and revised scaling equations to bring this lost giant back into our models of Jurassic ecosystems. But without the original bone, every reconstruction remains contested. Were Cope's measurements slightly off? Was the vertebra misidentified or even misdrawn? Each possibility shrinks or inflates the animal, and with it, our sense of the upper limits of dinosaur size? This unresolved puzzle prepares us to ask a deeper question. When the evidence is this fragile, how far can we trust any record-breaking claim? When all we have is a sketch, every millimeter matters. From that fragile outline of a single vertebra scientists tried to conjure one of the biggest creatures to ever walk the earth. To understand how, we need to see how paleontologists turn one bone into a whole body. They begin with scaling relationships, comparing the mysterious vertebra to those of better-known sauropod giants like Diplodocus or Supersaurus. If a mid-back vertebra in a known species belongs to an animal 25 meters long, and the sketched Amphicoelia's vertebra appears twice as tall, a first simple estimate might double the body length. Not just big animals, but potential titans approaching 50 or even 60 meters, stretching beyond a world of scale we can barely imagine. But the process does not stop at a single ratio. Researchers also assume a body plan. How long the neck should be relative to the torso, how many vertebrae the tail carries, how deep the chest is. They may plug measurements into statistical models built from dozens of sauropods, where vertebral height predicts overall mass, much as limb bone thickness does in other dinosaurs. Each equation quietly encodes an assumption that this lost vertebra belonged to a typical, long-tailed, long-necked sauropod, and not to some strange outlier. Join us as we step back hundreds of millions of years in the scientific imagination and watch those assumptions change through time. In the late 19th and early 20th centuries, Amphicoelius fragilis was drawn as a colossal, almost mythic creature, dwarfing even the largest Jurassic neighbors. Popular illustrations showed it towering over Brachiosaurus, its back a moving ridgeline on the ancient horizon. Later, as more complete giants like Argentinosaurus and Patagodon were described, some reconstructions pulled back, placing Mara Apunisaurus within a more conservative, though still massive, size range. A few modern studies even suggest that, depending on how we correct the sketch, it might overlap ordinary titanosaurs rather than utterly surpass them. Where do these differences come from? They arise from layers of potential error. The original bone might have been mismeasured in the field. The sketch itself could exaggerate the height of the neural spine or compress the proportions. Taphonomic forces, pressure, erosion, partial breakage, may have stretched or crushed the vertebra before it was ever drawn. If the bone was not a mid-back vertebra at all, but from the hip region or the base of the neck, every scaling equation built on that misidentification collapses. This leaves us with a dilemma. We want to know the upper limits of dinosaur size. We want to crown a single champion of the Mesozoic era. Yet scientific responsibility demands extreme caution when the evidence is a lost bone filtered through one 19th century drawing. How far should we let that phantom vertebra shape our record books, and how much should we let it go? In the next section, we will see how similar fragments have created and erased entire species of giants. And sometimes, that phantom bone is not just lost in a museum drawer. It is lost to the monsoon rains. In the late 20th century, on a low jungle-fringed outcrop in southern India, a small team of paleontologists worked in the mud as dark clouds gathered overhead. Before humans, before cities, before history itself, this place had been part of a vast river plain where giants wandered. Embedded in the weathered rock, they uncovered fragmentary remains, pieces of vertebrae, parts of a pelvis, and one massive element interpreted as a limb or hip bone of a sauropod of extraordinary size. From these fragments, they named a new dinosaur, Bruhathcaosaurus, literally huge-bodied lizard. In early reports, its dimensions were scaled up using better-known titanosaurs, producing estimates that rivaled or even exceeded Argentinosaurus. Here, it seemed, was another contender for the title of the biggest creatures to ever walk the earth, rising not from the famous Badlands of Patagonia, but from the humid hills of the Indian subcontinent. For a moment, the focus of gigantism shifted, hinting that this ancient world of scale we can barely imagine might have harbored multiple scattered lineages of colossal titanosaurs. Yet almost immediately, doubts began to grow. The bones were poorly preserved, heavily weathered, and coated with minerals. Some researchers looking at the published photographs wondered, were these truly dinosaurian at all? Could the limb bone be a petrified tree trunk, its internal structure disguised by decay and mineralization? Others suggested that, if it was bone, it might belong to a different kind of large reptile, or even to a misinterpreted mixture of animals. When the surface of a fossil is crumbling, when the internal texture is unclear, how confident can we be in any identification? Compounding the problem, the original material did not survive. Reports from later visits to the site describe the bones as having been destroyed or severely eroded by tropical weather, leaving only photographs, measurements, and field notes. Just as Amphicoelius fragilimus is now a story told through one 19th century drawing, Bruhathkaiosaurus became a story told through a handful of images and memories from a rainy field season. Once again, the primary evidence for a record-breaking giant slipped beyond our reach. Despite this, Bruhathkaiosaurus still appears in popular lists and online graphics, its silhouette stretched across screens with speculative lengths and masses. The name persists, echoing through documentaries and articles long after many specialists have moved on or labeled it dubious. One ambiguous bone, one eroded outcrop, and suddenly our picture of maximum dinosaur size tilts toward uncertainty. What happens when dozens of such fragments accumulate across the literature? In the next section, we will see how these scattered bones can inflate diversity, distort size records, and even conjure entire lineages that may never have existed at all. Those scattered bones do not just blur the record on paper. In the field, they can be woven together into giants that never truly walked the earth. To see how, we step back hundreds of millions of years in our minds, then descend into a very real quarry in western Colorado during the 1970s and 80s. Here, in the Morrison Formation, crews chipped and blasted their way through ancient river sediments laid down in the late Jurassic period. This was already a landscape of giants, home to Brachiosaurus, Diplodocus, and other colossal sauropods. But in one quarry near Dry Mesa, they uncovered something that seemed to eclipse even those record holders. An immense shoulder girdle, a fused scapula and coracoid, nearly 2.5 meters long, not just a big bone, but a massive slab of anatomy that suggested one of the biggest creatures to ever walk the earth. At first, this scapulocoracoid was heralded as evidence of a new supersauropod. It was informally called Ultrasaurus, later renamed Ultrasauros. Size estimates ballooned. Popular books spoke of a dinosaur that might have weighed more than any known brachiosaur, stretching the upper limits of what land animals could support. Around it, other isolated bones from the quarry were folded into the same narrative. Vertebrae, ribs, limb fragments, all pressed into service to flesh out a single spectacular skeleton. But rock does not lie, even when our interpretations do. As paleontologists returned to these fossils with more careful comparative anatomy, a different picture emerged. The famous scapulocoracoid, once thought to be beyond anything known, fell neatly within the range of a large but ordinary brachiosaurid, closely comparable to Brachiosaurus itself. Some of the vertebrae used to scale up Ultrasauros turned out to belong to a distinct diplodocid, later recognized as Supersaurus. Other bones represented yet another sauropod taxon from the same quarry. Piece by piece, the chimera unraveled. What had been presented as one ultramassive individual was in fact a jumbled assemblage of several large dinosaurs, preserved together by chance in the same ancient floodplain. Some of those animals were already named. Others would receive their own identities. Ultrasauros, as a distinct giant, dissolved into a tangle of synonyms and reassigned specimens. Why did this happen? When we stand in a quarry surrounded by isolated gigantic bones, the temptation is to connect them, to let our minds assemble a single colossal body out of scattered parts. Fragmentary material, confirmation bias, and the desire to push size records all set the stage for such mix-and-match creations. Only later, through painstaking reanalysis, do researchers separate each bone by shape, by microscopic texture, by exact layer in the rock, and discover that the one animal never existed. Ultrasaurus is not just a cautionary tale about one name. It is a warning about a world of scale we can barely imagine, where even experts can be seduced by magnitude. Join us as we follow this thread further into other claimed supergiants built from single bones and ask, how many of our record-breaking dinosaurs are really chimeras in disguise? To understand how those chimeras arise, we need to look at something subtler and in many ways more dangerous than a single mistaken giant. Not every error is as obvious as Ultrasaurus. Some hide behind respectable names that quietly swallow bone after bone. Paleontologists have a term for this, the wastebasket taxon. A wastebasket taxon is a species or genus that, over time, becomes a catch-all label for fragmentary or poorly understood fossils that look vaguely similar but may, in reality, represent several very different animals. In the early rush to catalog the ancient world, these names seemed useful. They let researchers file mysterious bones somewhere. But that convenience came at a cost. To see how, we step back hundreds of millions of years in scientific history to the dawn of dinosaur studies. Megalosaurus, one of the first dinosaurs ever named, began as a handful of teeth and bones from Jurassic England. As the 19th century unfolded, any large carnivorous bone from roughly the right rocks could be called Megalosaurus. Hip fragments, isolated vertebrae, teeth from different regions and different periods were all poured into the same conceptual bucket. The result was an animal that never truly existed, a blurred composite rather than a single lineage. The same fate befell Iguanodon. Originally described from distinctive teeth, it soon became the default name for a wide array of medium to large herbivorous bones across Europe. A thumb spike here, a jaw there, a partial limb somewhere else. All were drawn into the orbit of Iguanodon. When one bone becomes the anchor point, and that bone is poorly described or not truly diagnostic, every later resemblance, however superficial, becomes an excuse to reuse the name. A single misinterpreted fragment can, in effect, set the stage for decades of confusion. This is where one-bone diagnoses feed taxonomic chaos. Imagine an isolated vertebra named as a new species, based on size and a few ridges in the bone. Later, another vertebra of similar size appears in a nearby quarry. It is tempting to say they belong together. Then a rib, then a hip fragment, then a tooth that looks about right. Piece by piece, a wastebasket grows. On paper, the biggest creatures to ever walk the earth seem well represented. In reality, we may be merging several giants into one, or inflating a modest animal into a colossal phantom. Modern paleontologists now spend years dismantling these historical wastebaskets. Through detailed comparative anatomy, careful stratigraphic work, and computer-based evolutionary analyses, they pull bones back out of old names. Some fragments are reassigned to better-known species, others are declared nomina dubia, dubious names with no clear diagnostic features. As this happens, diversity curves shift, family trees are redrawn, and the apparent rise and fall of dinosaur lineages can change dramatically. How many supposed peaks of giant evolution vanish once the wastebaskets are emptied? And how many hidden giants emerge only when we let those old names go? Join us as we follow that trail into the heart of the size records themselves. But emptying those wastebaskets reveals another quieter problem. Sometimes the names do not vanish into doubt, they collide with each other. In the fossil record of giants, shadows overlap, and we discover that two supposedly different colossi are, in fact, the same animal wearing different labels. In taxonomy, these doubled labels are called synonyms, different scientific names that actually refer to a single biological species. They usually arise when bones are described in isolation. One team names a massive vertebra. Decades later, another team names a partial skeleton from a nearby layer. Only when someone compares them carefully do the patterns line up, and we realize we have been counting one dinosaur twice. This is where the rules step in. Under the Code of Zoological Nomenclature, the first validly published name has priority. The earliest name stays. The later one becomes a junior synonym and is retired from formal use. It is a strict, almost legalistic framework, designed to bring order to an ancient world of scattered clues. Yet that order can feel brutal when a familiar name is suddenly stripped of its status. One-bone taxa are especially vulnerable. A single gigantic limb bone or vertebra may look distinctive when nothing else is known. As more complete skeletons emerge from the same region and period, those supposedly unique features often dissolve into normal variation within a better-known species. A fragment once hailed as a separate titan might simply be the hip of an already named sauropod, or the tail of a predator we thought we understood. For a time, this duplication inflates diversity. Charts of the Mesozoic era fill with extra lines, extra names, extra apparent bursts of evolution. We see a forest of species where there may only be a few towering trunks. When synonymy is recognized and names are merged, those curves sink back, and our picture of how many colossal dinosaurs walked the Earth changes overnight. The impact reaches far beyond technical catalogs. Museum halls must be relabeled. That massive mount you visited as a child may quietly shift from one Latin name to another, its story rewritten while the bones themselves do not move an inch. Scientific papers that once compared two giants may now be reinterpreted as describing different individuals of the same lineage. Even popular books and documentaries must adjust as beloved names disappear into the footnotes of synonymy. And emotionally, there is a sense of loss. We form attachments to these names, to the idea that each one represents a distinct giant from a world of scale we can barely imagine. When they merge, it can feel as though a dinosaur has gone extinct for a second time. Yet behind that loss lies a deeper gain, a sharper, more honest view of ancient life. The real question is, what happens when synonymy strikes at the very biggest creatures to ever walk the Earth, and the record breakers themselves begin to blur? When even the record breakers begin to blur, we reach a kind of taxonomic twilight. Not quite discovery, not quite extinction. This is where a quiet but powerful label steps in. Nomen dubium, the dubious name. In formal zoological nomenclature, a nomen dubium is a warning sign built into the language of science. It means a species was named on material so incomplete, so non-diagnostic, that we cannot confidently match any new fossils to it. The name still exists on paper, anchored to its original type specimen, but it has lost its guiding power. It no longer tells us with any certainty what creature actually bore that name on the ancient Earth. To understand why, we have to look closely at the bone that starts it all, the holotype. This single specimen, sometimes just one vertebra or a fragment of limb, legally defines a species. For that bone to be truly diagnostic, it must show a clear anatomical identity, be preserved well enough to study in detail, and display a unique combination of features not seen in close relatives. Deep grooves, unusual proportions, distinctive joint surfaces, the exact shape of a neural spine, or the locking surface of a joint. These are the subtle signatures paleontologists search for when they try to separate one giant from another. But what happens when the type bone is too generic or badly damaged or worn smooth by deep time? A mid-tail vertebra that could belong to almost any large sauropod. A partial femur whose key edges have flaked away. In those cases, even modern tools, CT scanning, 3D models, meticulous comparative anatomy, may not rescue the name. If no unique traits can be confirmed, the species slides toward that dubious status. Many one-bone dinosaurs now live in this limbo. Names based on isolated, undistinctive vertebrae or scraps of limb bone are widely regarded as nomina dubia, because no future discovery can be securely tied back to them. The original bone still sits in a drawer, still technically defines the name, yet the name itself is effectively frozen in place. Scientists avoid using it in serious analyses because it cannot be applied to new material without guesswork, and guesswork distorts our picture of dinosaur evolution. This creates a real tension. Do we preserve every historical name out of respect for the pioneers of our field? Or do we clear away those that no longer help us understand this colossal age? Declaring a nomen dubium can feel like erasing a piece of scientific heritage. Yet it also frees us. It allows new specimens to be described under fresh, better defined names, to be placed accurately on the dinosaur family tree, and to set the stage for a cleaner, sharper view of diversity through the Mesozoic era. Join us as we follow this thread forward and ask, when the biggest creatures to ever walk the earth are known from only a single, uncertain bone, how do we decide whether to keep the name alive or let it fade into the background of a world of scale we can barely imagine? To answer that, we now turn from dusty drawers and old labels to beams of invisible light. In a quiet room full of humming machines, a single fossil bone slides into the core of a scanner, and we watch as its secrets are revealed layer by layer. This is the CT scan revolution in paleontology. Instead of sawing into priceless specimens, we can peer inside them, using high-resolution CT and even micro-CT to build three-dimensional maps of their interiors. We see growth rings, like those in trees, marking seasons of rapid and slow growth. We see networks of tiny canals where blood vessels once threaded through living tissue. In some bones, we see great dark voids, pneumatic cavities where air sacs invaded the skeleton, lightening it for a massive, active animal. Before humans, before cities, before history itself, these internal architectures evolved as silent records of life histories, not just outer shapes, but deep structure. Dinosaurs so massive their bones stretched longer than buses still carried microscopic patterns that differ from group to group. Join us as we use those patterns to test whether a lonely bone really belongs to a sauropod, a theropod, or something else entirely. Different dinosaur lineages leave different histological fingerprints. Many sauropod giants show dense, fibrolamellar bone with abundant growth marks, a signal of rapid, sustained growth. Bird-like theropods often combine that rapid growth fabric with complex pneumatic chambers, reflecting air sac systems similar to modern birds. Even the arrangement and thickness of internal struts, or trabeculae, can hint at how a limb or vertebra bore weight in a world of scale we can barely imagine. When the external surface is eroded or incomplete, these internal clues can narrow identity in ways 19th century scientists could never have dreamed. Consider a once ambiguous vertebra from a South American giant, long thought to represent an unusually colossal, deep-bodied sauropod. Early descriptions focused on its outer shape alone and inflated its size estimates. Decades later, CT scans revealed a remarkably bird-like web of air spaces inside, more like those of titanosaurs than of earlier sauropods, and showed stress patterns that fit a tail vertebra rather than the back. With that reinterpretation, its place in the skeleton shifted, its mass estimates dropped, and its supposed distinctiveness as a separate species weakened. A name built on one bone suddenly looked less secure. Yet even this technological leap has limits. Some fossils are so heavily mineralized that X-rays barely penetrate, leaving only ghostly outlines. Others are crushed, stretched, or fractured by the pressures of deep time, scrambling their internal architecture beyond recognition. And even a perfectly scanned bone is still just one piece of a missing body. CT data can suggest relationships, growth rates, and breathing systems, but it cannot conjure skulls, limbs, or armor that were never preserved. So where does that leave our one-bone species, poised between validity and oblivion? As we move forward, we will see how CT images combine with 3D modeling, field geology, and comparative anatomy to decide which names endure. and which fade into the background of the Mesozoic record. CT data gives us the inside of the bone. But in the last 2 decades, something equally transformative has emerged for the outside. With 3D surface scanning and high-resolution photogrammetry, a fragile fossil can be turned into a detailed digital mesh, a precise ghost of stone floating in virtual space. Before humans, before cities, before history itself, the Earth belonged to giants. Today, on our computer screens, we can rotate a single vertebra from that ancient world as if we held it in our hands, zooming into every ridge and groove without risking a single crack. Multiple overlapping photographs or a laser sweeping across the surface capture millions of points, building a mesh that can be measured to the fraction of a millimeter and shared worldwide in seconds. This is where our one-bone species enter a world of scale we can barely imagine. A lonely sauropod hip or theropod toe can be imported into a digital lab and virtually overlaid onto complete 3D skeletons of better-known dinosaurs. Does the curve of that vertebra match the sweeping backbone of Diplodocus? Or does it fit more closely against the massive, high-shouldered frame of Argentinosaurus? When we resize the mesh to plausible proportions, does it articulate cleanly with neighboring bones? Or do gaps and collisions reveal a poor anatomical fit? Join us as we use these digital clones to test long-standing claims. A proposed giant femur can be aligned with the hind limb of Patagotitan to see whether its joint surfaces meet naturally, or whether the angles suggest a different clade altogether. By comparing curvature, muscle scar positions, and overall proportions, paleontologists can ask, in a precise, quantitative way, whether a one-bone holotype truly belongs among the biggest creatures to ever walk the Earth, or whether earlier estimates pushed it beyond what the anatomy can support. Beyond simple overlay, virtual articulation opens a new frontier. In software, researchers can hinge bones around realistic joint axes, adjusting angles to reconstruct walking, rearing, or tail-swishing postures. They can map inferred muscle attachments onto the digital surface, then run stress simulations to see how forces would travel through the bone during a step or a neck sweep. Does the cross-sectional strength of that fragment make sense for a 70-ton giant? Or does it behave more like the limb of a smaller, more lightly built dinosaur? Because these fossils are digital, collaboration scales up dramatically. A single one-bone type specimen, scanned once, can be examined in detail by teams on different continents, each bringing their own comparative collections and analytical tools. Disagreements play out on the same shared mesh, not on fuzzy photographs or secondhand drawings, and over time that global scrutiny helps strip away misidentifications and refine which names will endure. In the next step, we will see how these virtual skeletons, combined with field geology and evolutionary trees, set the stage for revisiting some of the most controversial giant species ever proposed. Those virtual skeletons only tell half the story. To truly know what a lone bone represents, we have to know when and where in deep time it was laid to rest. Before humans, before cities, before history itself, rock layers were quietly recording the rise and fall of giants, not just isolated snapshots, but stacked chapters. When paleontologists walk a cliff face or an eroded badland, they read those layers the way you might read the pages of a massive history book, each bed of sandstone or mudstone a line in the chronicle of the Mesozoic era. This is stratigraphy. A bone found below one layer and above another is pinned between two dates, especially if those layers include volcanic ash beds that can be radiometrically dated to the nearest few 100,000 years. Add in index fossils, like distinctive ammonites or tiny marine invertebrates with well-known time ranges, and we can often say not just Jurassic or Cretaceous, but a precise slice of a period, narrowed to a few million years. Why does that matter for a single mysterious vertebra or limb bone? Because once we know its exact horizon, we can compare it with every other fossil from that same time slice and region. If a lone sauropod vertebra comes from an Upper Jurassic formation already rich in well-known species, the range of plausible identities shrinks dramatically. Instead of imagining every giant that ever walked the Earth, we ask a sharper question. Which dinosaurs are actually documented from this age, on this continent, in this formation? Sedimentology then adds another layer of constraint. Join us as we step back hundreds of millions of years and picture the environments these rocks represent. Some beds were carved by river channels, full of coarse sand and pebbles, where heavy limb bones from colossal sauropods might accumulate. Others are fine floodplain muds, ideal for preserving lighter, more delicate skeletons, or coastal lagoons and deltas where marine reptiles mix with dinosaurs washed in from shore. A bone entombed in an ancient river channel suggests a different community than one sealed in a quiet lake bottom. Yet the rock record is not always honest. Bones can be reworked, eroded out of older strata, and transported into younger sediments, like ancient relics dropped into the wrong chapter of Earth's story. A Cretaceous river might tear fossils from Jurassic beds upstream and redeposit them far from their original home. Without careful field mapping, grain size analysis, and even geochemical fingerprints comparing bone to surrounding matrix, we could misplace a species in time and invent false patterns of evolution or extinction. So when a lone bone challenges size records or hints at a new lineage, our first task is not to imagine its body, but to anchor its place in the stratigraphic book. Only then can we ask the next, more dangerous question. Does its anatomy truly demand a new name? Or is it an echo of a giant we already know? In the following section, we will see how evolutionary trees test those possibilities and how some legendary one-bone giants begin to vanish when time and anatomy are weighed together. To weigh those possibilities, paleontologists do something deceptively simple and quietly radical. They drop that lonely bone into an evolutionary family tree and see where, if anywhere, it fits, not by imagination, but by numbers. In modern phylogenetic analysis, every species is broken down into characters, tiny anatomical questions scored in a matrix. Is this joint surface rounded or flat? Are the muscle scars sharp ridges or broad swells? Is the bone shaft more like a column or a blade? Each answer becomes a 0, 1, or 2 in a vast table that may span hundreds of traits and dozens of dinosaurs, from small Triassic forms to the biggest creatures to ever walk the Earth. Once that matrix is built, algorithms search for evolutionary trees that require the fewest changes in those characters over time. This is the principle of parsimony. The result is not a single picture, but a forest of possible trees, each showing clades, branches of closely related species that share inherited features. When many trees agree, we gain confidence that we are seeing real patterns in dinosaur evolution, rather than noise. So where does a single bone enter this colossal framework? Even one vertebra or femur can offer a surprising number of scoreable traits. The shape of the articular surfaces can hint at posture and movement. The pattern of pits and ridges can trace ancient muscle attachments. The proportions of the bone, its curvature, and the presence of internal air spaces can all be coded and compared to larger datasets built from more complete giants. Join us as we imagine a fragmentary sauropod vertebra, long and airy, with deep cavities carved into its sides. When we code those features and run the analysis, the algorithms may nest it among titanosaurs or pull it closer to diplodocids with their whip-like tails. On paper, the bone has found a family. In the matrix, it has a home. But there is a hidden cost. Most of the cells for that one-bone species are blank. Missing data means the analysis has very little to hold on to. Add or remove a few other taxa, or tweak the character list, and the bone's position can jump from branch to branch like a ghost, sometimes allied with one lineage, sometimes with another. Step back hundreds of millions of years in your mind, and you can feel how fragile this placement really is. Phylogenetics can set the stage for testing affinities, but it rarely settles debates about one-bone dinosaurs. Instead, it offers a range of plausible homes, each provisional, each vulnerable to the next discovery. What happens when a new skeleton emerges from the rock and collides with these delicate trees? In the next section, we will watch some famous giants shift, shrink, or vanish altogether. Sometimes those delicate evolutionary trees do not just wobble, they snap. And the break happens not in a computer lab, but in a dusty quarry where a new skeleton comes to light. Imagine we step back hundreds of millions of years to a Jurassic floodplain, then return to the present, where that same rock unit has been quarried for over a century. In the 1800s, a single massive vertebra was pulled from these beds and given a grand Latin name, hailed as one of the biggest creatures to ever walk the earth. That lone bone became the type specimen, the legal anchor for the species. For generations, it sat in a drawer, a symbol of a giant no one could quite see. Then, one field season, the rock yields something different. Not a fragment, a nearly complete sauropod skeleton, articulated from skull to tail, lying in the same formation, sometimes only a few meters away in the stratigraphic column. At once, that ancient name and this new body are forced into conversation. Could they be the same animal? This is where the detective work begins. Paleontologists carefully expose the corresponding bone in the new skeleton, the matching vertebra or femur or hip. They measure every ridge, every hollow, every curve. Does the new vertebra share the same proportions, the same unusual laminae, the same deep excavations that defined the original one-bone taxon? Or do subtle differences in shape, articulation, and internal structure reveal that we are dealing with two separate giants that simply died in the same ancient world? Sometimes the fit is extraordinary. The new skeleton's bone matches the type nearly detail for detail. In those cases, the old name is vindicated. A label coined in the age of gas lamps suddenly gains a skull, a rib cage, limb bones, even skin impressions. Museum mounts are relabeled, life reconstructions updated, and that once ghostly species now strides through documentaries as a fully fleshed giant. A dusty vertebra has become an entire animal. At other times, the story is more complicated. The new skeleton may clearly differ, showing that the one-bone species is distinct, yet still frustratingly incomplete. Or the comparison may reveal that the original bone was never diagnostic at all, its supposed unique features turning out to be common among many sauropods. In that moment, a name that stood for a colossal mystery for over a century can be downgraded to a dubious shadow. These reversals highlight the time lag baked into paleontology. Names coined during the bone wars of the 19th century or in the early 1900s can suddenly be re-evaluated in the light of 21st century discoveries and techniques. CT scans, 3D models, and dense comparative databases let us test matches in ways early workers could not have imagined. Overnight, a record-breaking giant might shrink into synonymy, or a neglected scrap might emerge as the key to a new lineage. Join us as we watch how these late-arriving skeletons set the stage for rewriting not just species lists, but the entire narrative of dinosaur gigantism in the next part of our journey into a world of scale we can barely imagine. Those late-arriving skeletons do more than tidy up museum labels. They reshape the graphs we use to tell the story of dinosaur life and death. When paleontologists talk about diversity, they are not just speaking in poetry, they are counting names. To track how many kinds of dinosaurs lived at any moment, researchers build diversity curves, rising and falling lines that trace species richness through time. We step back hundreds of millions of years, slice the Mesozoic into time bins, and ask a deceptively simple question: how many named species fall into each slice? Each point on that curve is built from type specimens, catalog numbers, and Latin names scattered across the scientific literature. But here's the problem. Many of those names rest on a single bone or a handful of fragments described a century or more ago. A lone sauropod vertebra from the late Jurassic, a partial femur from the early Cretaceous, a worn tooth from an obscure quarry. Each was once christened as a new species and folded into the count. Treat all of them as equally real, and the Mesozoic suddenly teems with giants. Diversity soars on paper, even if the rock record is whispering a quieter story. Modern revisions cut into that apparent richness. As experts re-examine old material, one-bone taxa often dissolve into synonymy or are declared dubious, nomina dubia, that no longer anchor distinct species. A supposed colossal sauropod from a single vertebra might be reassigned to an already known lineage. A fragmentary theropod hip might be recognized as an indeterminate predator, not a new kind of giant. When those names drop out of the dataset, dramatic spikes in diversity can flatten, and once sharp peaks become gentle hills. The timing of evolutionary radiations and declines depends on where those hills and valleys sit. Did sauropods explode in diversity early in the Jurassic? Or does that surge vanish when we strip away fragile one-bone species? Did certain groups of the biggest creatures to ever walk the Earth begin to fade long before the end Cretaceous impact? Or does that apparent decline simply reflect a tangle of dubious names being pruned unevenly through the record? Our answers can shift with every taxonomic revision. This matters because we use those curves to tackle the grandest questions of this ancient world. How quickly did dinosaurs rebound after earlier mass extinctions? How crowded were ecosystems at their peak, and how vulnerable were they when catastrophe struck? If the very names behind each data point are unstable, how confident can we be in any sweeping narrative of rise, dominance, and extinction? Join us as we follow those fragile lines of evidence forward and ask, when we correct for these mirages of diversity, what does the true silhouette of dinosaur history look like? And how does it reshape our search for a world of scale we can barely imagine? When those silhouettes harden into numbers, the stakes rise even higher. Because in the public imagination, there is one question that towers over all the rest. Which dinosaur was the biggest of them all? Not just big animals, but true titans. The biggest creatures to ever walk the Earth. Names like Amphicalius fragilis, now often called Mara-Apunisaurus, Bruhathkaiosaurus, and other proposed super titanosaurs have headlined articles and museum displays, each announced as a new record breaker. Yet when we look behind the headlines, we often find a single vertebra sketched in the 1870s and now lost, a few weathered limb fragments from India, or an isolated hip bone that may not even belong to a dinosaur. The foundations of these colossal records are, in many cases, astonishingly fragile. Amphicoelius fragilis was once reconstructed at over 50 meters long, based on one towering dorsal vertebra described by Edward Cope. That bone has vanished. All that remains are measurements and a drawing, filtered through 19th century methods and assumptions. Bruhathkaiosaurus, hailed as even larger, is known from fragmentary remains that deteriorated in storage and were never fully documented with modern techniques. Other giants, from outsized tibiae to partial tails, hover at the edge of plausibility, their sizes extrapolated far beyond what the fossils can securely support. Yet these are the names that media outlets and popular books often seize upon. A lost vertebra that might imply a 100-ton animal makes for a striking headline, even if the estimate rests on a chain of assumptions. Superlatives attract attention. They promise a world of scale we can barely imagine. And in an era of rapid news cycles and viral images, the most extreme numbers tend to win. How often do we see the cautious footnotes, the phrases like, if correctly identified, or based on very limited material, carried over into those stories? In contrast, many paleontologists prefer to anchor their discussions of size in more complete, repeatable evidence. Argentinosaurus, Patagotitan, and Dreadnoughtus are still fragmentary, but they preserve multiple limb bones, vertebrae, and hips, allowing different teams to build independent 3D models and compare results. These giants may or may not be the absolute largest, yet they give us something more valuable than a record. They give us testable data about how such bodies were built, how they grew, and how they moved through their ancient world. So should we crown record holders at all, when so much rests on single bones, lost specimens, and extrapolations at the edge of our methods? Or should we, instead, treat largest dinosaur ever as a moving hypothesis, one that shifts as new fossils emerge and old claims are re-examined? Join us as we follow this tension between spectacle and skepticism into the next layer of the story, where the race for the biggest collides with an even deeper question. What do we really want from these giants of deep time? And what might we be missing when we chase only the extremes? To feel that tension, we have to watch something almost magical happen. A single silent bone turning into a living giant on the page. Not through fossils alone, but through the partnership between scientists and artists who dare to imagine a body from a fragment of a spine. When a museum or research team commissions paleo art for a one-bone species, the process does not begin with wild fantasy. It begins with relatives. Paleontologists first ask, where on the dinosaur family tree does this vertebra most likely belong? If it resembles the backbone of a titanosaur like Argentinosaurus, or a diplodocid like Supersaurus, that comparison quietly sets the stage for everything that follows. The artist studies those better-known skeletons, copies their basic proportions, then stretches or compresses them to match the scale implied by the new bone. From there, the work becomes a careful negotiation. The lone vertebra dictates certain constraints. Its height and width hint at overall size. Its robustness suggests how heavily muscled the torso might have been, and its features reveal whether it came from the neck, the back, or the base of the tail. A towering dorsal vertebra might imply a deep, massive body. A slender neck vertebra might suggest a long, elevated feeding reach into a world of scale we can barely imagine. Yet beyond that anchor point, the unknowns multiply. What did the head look like? How long was the tail? Was the body barrel-shaped or lean? Here, interpretation rushes in to fill the gaps. Artists and scientists debate posture. Do we show a horizontal whip-like tail or a gently drooping one? A neck sweeping high over the canopy or held more modestly at shoulder height? They sketch musculature based on modern analogs. Birds, crocodiles, even elephants, layering flesh over hypothetical bones. Skin texture, color patterns, and any armor or display structures are chosen from a palette of plausibility rather than proof. Step back hundreds of millions of years, and we are still, in many ways, painting in the dark. Yet once that painting is finished, something powerful happens. A speculative vertebra becomes a colossal, fully lit sauropod, striding across a Cretaceous floodplain. For viewers, that image can feel as concrete as the skeleton of Diplodocus in a gallery. The feedback loop begins. The more striking the artwork, the more real the one-bone species seems, and the more it circulates in books, documentaries, and online, the easier it is to forget how fragile the evidence truly is. How often do we remember, looking at these giants, that the entire edifice rests on a single fossil clue? This is why responsible paleoart matters so deeply. Clear labels, captions, and narration that state hypothetical reconstruction based on one vertebra do not diminish the awe. They deepen it by inviting us into the process rather than hiding the uncertainty. Join us as we follow these ghostly giants from canvas back to stone and ask what happens when new discoveries confirm or shatter the bodies we have imagined for the biggest creatures to ever walk the earth. But there is another problem lurking inside those ghostly outlines. When all you have is a single bone, it is not just the body that is uncertain. The very name of the animal can begin to drift. In the language of paleontology, this is the problem of synonymy. different scientific names that in reality describe the same biological species. Under the rules of zoological nomenclature, each species is anchored to a holotype, a defining specimen. Sometimes that holotype is a nearly complete skeleton. Sometimes, especially from the early days of dinosaur hunting, it is just one vertebra, a partial hip, or a single limb bone. When such fossils are described in isolation, without the context of a full skeleton or a rich fossil bed, it becomes all too easy for separate teams in separate places to name the same animal twice. During the 19th and early 20th centuries, as we step back hundreds of millions of years through the rock record, this happened again and again. A massive sauropod limb from one quarry might be named as a new species. Decades later, a similar limb from another continent or another layer of rock would receive its own grand Latin title. At the time, it felt as if we were uncovering a parade of new giants. Yet without overlapping, comparable bones, no one could be sure whether these fragments actually matched material that had already been described. Only when more complete skeletons emerged did patterns start to appear. A new skull might slot perfectly onto the proportions implied by an old, lonely femur. A series of tail vertebrae could reveal that three supposedly distinct colossi, each known from a different part of the body, were in fact the same dinosaur seen from different angles. Names that once stood proudly as separate species were quietly demoted to junior synonyms, shadows of a single, better-known animal. The roster of the biggest creatures to ever walk the earth would shrink, not because the giants vanished, but because we realized we had counted some of them 2 or 3 times. This has profound consequences for how we read the history of life. Diversity curves that track dinosaur species through each era and period are sensitive to every name we add or remove. When synonymy is corrected, apparent bursts of evolution can flatten, and supposed peaks of variety can soften into more modest hills. Public lists of known species contract, museum labels change, and our image of Mesozoic ecosystems is reshaped, from teeming crowds of subtly different titans to a smaller cast of widespread, long-lived lineages. In a world of scale we can barely imagine, even a handful of miscounted names can distort the story of abundance and decline, of radiation and extinction. How many of the colossal silhouettes in our field guides are really duplicates wearing different labels, and how many represent truly distinct ways of being a giant on ancient Earth? Join us as we follow that mystery into the next layer of the rock record, where fragmentary bones do not just share names, but sometimes hide imposters from entirely different branches of the dinosaur family tree. When we try to sort out this crowd of names and lonely bones, we run into another problem left to us by the early days of dinosaur science. Before strict rules, before careful comparisons, some species became catch-alls. Not precise labels, but baskets, wastebaskets. In taxonomy, a wastebasket taxon is a broadly defined species or genus that, over time, absorbs almost any fossil fragment that looks vaguely similar. The definition stretches, the diagnosis blurs. Instead of sharpening our view of ancient life, these names smear it. During the 19th century, when the rush to name the biggest creatures to ever walk the earth was at its peak, this pattern became especially powerful. New bones poured into museums faster than scientists could analyze them in detail, and familiar names became convenient destinations. Megalosaurus is a classic example. Originally described from fragmentary jaw pieces and limb bones in England, it was one of the first dinosaurs ever named. For decades afterward, any large meat-eating dinosaur bone from the Jurassic of Europe that did not clearly fit something else could be filed under Megalosaurus. Vertebrae limb fragments, isolated teeth, sometimes from very different predators, all vanished into this single massive drawer. The name survived, but the real diversity of Jurassic theropods was hidden behind it. Iguanodon followed a similar path on the herbivorous side. First known from distinctive teeth and a handful of bones, it became a symbol of early dinosaur discovery. As the decades passed and more partial skeletons surfaced across Europe, many bipedal plant eaters with broadly similar teeth or hips were called iguanodon by default. Some belonged there, many did not. One-bone specimens, a thumb spike here or a femur there, were especially easy to sweep in because who could prove they were anything else? This habit created a quiet crisis. When isolated bones from different species are all assigned to the same broad taxon, it becomes almost impossible later to tell which fossils truly belong together. How many supposed giants, built from scattered remains, are actually mosaics of several animals? How many evolutionary stories, such as the rise of particular feeding strategies or locomotion styles, have been blurred because wastebasket taxa merged unrelated lineages into a single, misleading name? Today, paleontologists work to clean up these taxonomic messes. They revisit old collections, redescribe type specimens, and compare every ridge, socket, and joint surface in far greater detail. They ask whether the original name was based on unique diagnostic features or on traits shared widely across a whole group. If a genus like the old broad Megalosaurus cannot be clearly defined, its extra species may be split off, reassigned, or declared invalid, turning them into so-called dubious names. Stratigraphy, precise dating, and large-scale evolutionary analyses help decide whether scattered bones really represent one widespread animal or several distinct, regionally adapted forms. Join us as we follow this process into the next layer of the story, where cleaning out these wastebaskets does more than tidy our lists. It reshapes our sense of how many kinds of giants actually walked across that world of scale we can barely imagine, and it forces us to confront an even sharper question. When a name is swept away, what happens to the record-breaking titan it once described? And nowhere is that question sharper than in the saga of the Jurassic giants we once thought we knew. When we step back hundreds of millions of years into the Morrison Formation of Western North America, we enter an ancient floodplain littered with colossal bones, many of them isolated, scattered by rivers and time. Before humans, before cities, before history itself, this landscape belonged to giants, not just big animals, but true titans, with vertebrae taller than a person and shoulder blades longer than a car. In the late 20th century, as teams uncovered massive bones from these rocks, it seemed as if we were adding one record breaker after another to the roster of the biggest creatures to ever walk the earth. At Dry Mesa Quarry in Colorado, excavators pulled out a huge shoulder blade and immense vertebrae from different parts of the site. The shoulder blade, towering and broad, was unlike the familiar diplodocids. The vertebrae, elongated and lightweight, hinted at a different kind of sauropod design. Because these bones were not clearly connected in the ground, early workers treated them as belonging to separate, equally spectacular animals. The long, elegant tail vertebrae were assigned to a new dinosaur named Supersaurus, a diplodocid so extended in length that it seemed to stretch the limits of what a land animal could be. The gigantic shoulder blade and some limb bones were named Ultrasauros, promoted as an even larger, brachiosaur-like giant. Two names, two supposed champions, both drawn from a patchwork of isolated bones. How could anyone resist imagining two separate monsters ruling that Jurassic ecosystem? As more quarries were opened and more comparative anatomy was done, the picture began to change. Detailed studies showed that several of the bones used for Ultrasauros did not truly form a coherent skeleton. The famous shoulder blade turned out to be from a large but ordinary brachiosaurid, probably Brachiosaurus itself. Other elements matched Supersaurus, meaning they had been split between two names that described the same kind of animal. Piece by piece, Ultrasauros was stripped of its uniqueness. Under the rules of zoological naming, it became a junior synonym and was effectively sunk, while Supersaurus remained the valid genus tied to the distinctive diplodocid vertebrae. What looked like two different record-breaking dinosaurs collapsed into one very long, very impressive, but no longer unprecedented giant. This revision rippled outward. Charts of largest dinosaurs ever had to be redrawn. Some supposed size gaps between brachiosaur-type sauropods and diplodocids narrowed or disappeared, and we were left with a sobering lesson. When single vertebrae and isolated limb bones are found separately, in a world of scale we can barely imagine, they can easily be overinterpreted as multiple, never-before-seen colossi. So if one quarry could inflate our giant count by splitting one animal into two, what happens when the only evidence for a supposed titan is a single, fragile bone, and sometimes not even a bone we still possess? In those cases, the fossils do not just blur together, they begin to vanish as distinct creatures. In the language of paleontology, many of these one-bone titans slip into a special kind of scientific ghost story. They become a nomen dubium. A nomen dubium, literally a dubious name, is a species label based on materials so poor, so incomplete, or so plain that we cannot reliably tell it apart from other, better-known dinosaurs. The bone might be real, the age and rock layer might be clear, but if that fragment lacks unique features, it fails the most basic test of identity. Is this vertebra, this toe bone, this scrap of hip, truly different from dozens of other giants that walked the same ancient floodplains? If we cannot answer that with confidence, the name is in trouble. Single bones are especially vulnerable. A lone tail vertebra from a colossal sauropod can be massive, yet still look almost interchangeable with those of its close relatives. A femur might tell us the animal was one of the biggest creatures to ever walk the earth, but not which lineage it belonged to. When early fossil hunters named species from such fragments during the frantic races of the 19th century, they unintentionally set the stage for a future reckoning. As more complete skeletons appeared, many of those proud names could no longer stand on their own. Declaring a nomen dubium does not mean the fossil disappears. The bone is still there in its museum drawer, still a real piece of Earth's history, still a data point in the story of dinosaur evolution. What changes is its legal and scientific role. It loses its power to anchor a species concept. That original fragment, the holotype, no longer defines a unique dinosaur. It is folded back into a broader, less specific category, such as indeterminate titanosaur or large theropod of this formation. For scientists and for all of us who grew up with dinosaur books, that loss can feel personal. A name we learned, imagined, and perhaps pictured as a towering silhouette on the horizon is suddenly labeled doubtful. Another giant, gone from the tally. Yet this pruning is not an act of destruction. It is an act of clarification. By stripping away names that rest on shaky foundations, we strengthen the reliability of the fossil record and sharpen our view of true diversity through the Mesozoic era. So what happens to our picture of a world of scale we can barely imagine when several record-breaking species are demoted to mere fragments in the crowd? And could some lost bones still be rescued from this limbo? Some of those fragments in limbo can never be rescued, but others still hold secrets, locked not on the surface of the bone, but deep inside. To reach them, we do not need a chisel. We need a hospital. In the last few decades, CT scanners have become one of the most powerful tools in dinosaur science. Instead of slicing a priceless vertebra or limb bone, we can pass it through a ring of X-rays and build a detailed three-dimensional map of its interior. We see density changes, hidden cavities, and delicate internal walls that would have been destroyed by older methods. Suddenly, a single broken vertebra is not just an outline, it is a cross-section of an entire way of life. This matters because the biggest creatures to ever walk the earth did not just grow larger on the outside. Inside their bones, evolution carved out complex patterns of air sacs, blood vessels, and strengthening struts. Many sauropods had pneumatic or air-filled vertebrae, riddled with chambers linked to a bird-like respiratory system. Certain theropods show distinctive arrangements of vascular canals and marrow spaces. Ornithischians often keep their bones more solid, with different textures of supporting tissue. When we step back hundreds of millions of years with a CT scan, these inner architectures can reveal which great clan a mystery bone belonged to. Join us as we follow a few of these rescues. In South America and Africa, isolated giant vertebrae once labeled only as indeterminate dinosaur have been scanned and shown to contain the intricate honeycomb of air spaces seen in titanosaurs. That internal pattern, combined with the age of the rocks, allowed paleontologists to say with new confidence, this fragment really was part of a colossal long-necked herbivore. In other cases, limb bones thought to be from massive carnivores were CT scanned and found to lack the extreme pneumaticity of advanced theropods, pushing them instead toward more ordinary, heavy-boned ornithischians. One partial tail vertebra from the late Jurassic of North America, long debated, illustrates the power of this approach. On the outside, it could have belonged to almost any large dinosaur. Inside, CT slices revealed complex internal buttresses and air canals matching known diplodocid sauropods. The bone did not justify a new species, but it did anchor that lonely fossil within a real family tree. Yet even this technology has limits. Some bones, especially from smaller dinosaurs, are only weakly pneumatic or have generalized vascular patterns that overlap across groups. Mineralization during fossilization can blur or erase fine internal details. CT data might tell us we are looking at a large sauropod, but not which lineage, and certainly not whether this vertebra deserves its own name. Many one-bone taxa remain ambiguous because their inner anatomy is simply not distinctive enough. So where does that leave our attempts to measure giants and rewrite size records from fragments alone? And what other techniques can we combine with CT scans to narrow the possibilities even further? To push beyond what a single bone can tell us, we now invite that fragment into the digital realm. Instead of guessing with pencil sketches and tape measures alone, we can scan a lonely vertebra or limb bone in 3 dimensions and let it speak to us with unprecedented detail. High-resolution 3D scanning captures every ridge, cavity, and curve of an isolated fossil. Once that digital twin exists, we can slide it, rotate it, and virtually dock it against complete skeletons of related giants. Does this sauropod vertebra match the proportions of Diplodocus? Or does it sit more comfortably inside a Brachiosaurus-style backbone? By overlaying the scan onto known species, scaling and aligning them in software, we can test which family tree branch it most likely belongs to, instead of relying on memory or hand-drawn comparisons. From there, scaling techniques take over. Paleontologists have spent decades measuring how certain bones relate to overall body size, the circumference of a femur, the length of a humerus, the height of a dorsal vertebra. When we feed those relationships into a digital model, a single bone can set the scale for an entire virtual skeleton. If a vertebra from a patagotitan-like animal is 20% larger than the same vertebra in the original skeleton, we can grow that whole model by 20%. Then ask, what does that do to length, height, and mass? Virtual skeletons let us go further still. In the computer, we can mirror left side bones to rebuild missing right side elements, or splice together a composite animal from several better-known relatives that share the same general body plan. Join us as we adjust neck length, tail thickness, or chest depth, watching the outline of a colossal herbivore swell or slim on screen. Each variation becomes a testable hypothesis about posture, center of mass, and how such a body would have moved across the ancient Earth. This is where we step into a world of scale we can barely imagine, but also one we can measure with new rigor. Software can wrap these digital skeletons in simulated flesh, calculate volumes, and then convert those volumes into mass estimates under different assumptions about muscle and fat. Instead of a single dramatic number for the biggest creatures to ever walk the Earth, we get ranges and probabilities, perhaps 50 to 70 tons, perhaps 30 to 40 meters long. depending on which plausible body plan we choose. Yet for one bone species, these reconstructions are powerful and precarious at the same time. Every model rests on choices about which relatives to use, how to scale them, and how much soft tissue to add. Change those inputs, and the giant on our screen swells or shrinks. So how do we keep these digital dinosaurs honest and avoid building beautiful illusions from fragile evidence? One of the most powerful ways to test those beautiful illusions is not with more pixels, but with more rocks. Before we can trust a digital giant, we have to ask a very simple question. Exactly where in Earth's layered skin did that lonely bone come from? This is where stratigraphy enters the story. Stratigraphy is the study of rock layers and their sequence through time, a geological calendar written in stacked sands, muds, and volcanic ash. When we step back hundreds of millions of years, we do not just see dinosaurs in isolation. We see them anchored to horizons in the rock record, each layer marking a particular period, climate, and ecosystem. That context can be as important as the bone itself. If we know the precise horizon and formation where a bone was found, we can narrow down its identity dramatically. A single sauropod vertebra from the Morrison Formation in North America, for example, does not float in a timeless void. It comes from late Jurassic rocks, roughly 150 million years old, from an ancient world of floodplains and river channels, already crowded with well-known giants like Diplodocus, Apatosaurus, and Brachiosaurus. At that point, we can ask, does this fragment truly represent a new species? Or does it simply fall within the variation of dinosaurs we already know from that formation? The reverse is just as revealing. When the supposed age or environment of a one-bone dinosaur does not match its proposed relatives, alarm bells start ringing. Imagine assigning a fragmentary limb bone to a species otherwise known only from much younger Cretaceous rocks. If careful dating shows the fragment actually comes from older Jurassic strata, that temporal mismatch suggests a misidentification. How could a single species span tens of millions of years without leaving more complete remains in between? These checks are not theoretical. Detailed stratigraphic mapping has already forced scientists to rethink several massive one-bone taxa. Some vertebrae once hailed as record-breaking sauropods turned out, after re-examining their rock context, to come from different formations than originally reported. Once their true horizons were established, the pool of possible identities shifted. In a few cases, the bones were quietly reassigned to already named dinosaurs that share the same layer, age, and environment. In others, the combination of fragmentary anatomy and uncertain stratigraphy pushed them toward that uncomfortable label. Dubious name. Join us as we follow this logic to its full conclusion. If a bone's layer, age, and paleo-environment do not fit its supposed family, what else might be wrong with our reconstructions? Could some of the biggest creatures to ever walk the earth, celebrated in books and museum murals, be statistical ghosts created by mixing the wrong rocks with the wrong bones? In the next section, we will see how layering anatomical clues on top of this stratigraphic framework can further test which giants were real and which belong to a world of scale we can barely imagine. To answer those questions, we have to move from rocks to bones themselves and into a quieter kind of drama, the drama of shape. Before we can crown any fragment as one of the biggest creatures to ever walk the earth, paleontologists must decide what that fragment actually belongs to. This is where diagnostic characters come in. Not every bump or curve on a fossil is meaningful, but certain features act like anatomical fingerprints. A vertebra might have a particular pattern of deep air-filled pits, a neural spine that flares into a distinctive blade, or joint surfaces that lock together in a very specific way. The exact angle of an articulation, the height of a ridge, the outline of a process. These details can distinguish one group of giants from another, and sometimes one species from its closest relatives. To see those differences, experts do not work in isolation. They compare a candidate bone against massive reference collections in museums around the world and against detailed anatomical descriptions published over more than a century. Join us as we step back hundreds of millions of years in our minds while standing in modern collections, placing a new tail vertebra from South America beside sauropod bones from North America, Africa, or Asia. Does the pattern of laminae and cavities match Diplodocus or resemble titanosaurs like Argentinosaurus? Or does it fall outside any known variation? However, bones are not static objects stamped from a mold. Within a single species, there is intraspecific variation. Young dinosaurs had unfused joints and proportionally different limb and skull shapes. Males and females could differ in robustness or ornamentation. Individual health, injuries, and simple genetic quirks added more variety. A juvenile vertebra can look deceptively delicate. An elderly animal's bone can be remodeled, pitted, or arthritic. Without recognizing these stages, an odd bone risks being elevated to a new name instead of understood as part of a life cycle. History is full of such corrections. Supposed new sauropods based on a single oversized limb bone or vertebra have been quietly demoted when careful comparative work showed they fall inside the range of already known taxa. Some one-bone wonders have turned out to be juvenile individuals of familiar species, their unfinished surfaces mimicking exotic anatomy. Others, once hailed as colossal outliers, are now interpreted as elderly or pathological members of established lineages, rather than ambassadors from a world of scale we can barely imagine. This anatomical detective work does more than tidy labels. It filters illusion from signal, making sure our charts of diversity, size, and evolution are built on real differences rather than on age, sex, or chance deformity. In the next section, we will see how these carefully vetted bones are woven into family trees and how a single misread ridge or socket can ripple through our entire picture of dinosaur evolution and gigantism. Now that our names and labels have been tightened, we can finally ask a deeper question. Where in the grand story of evolution does that lonely bone actually belong? To answer that, paleontologists do not just trust their instincts. They plug these fragments into a powerful tool, phylogenetic analysis. In essence, a phylogenetic analysis is an attempt to rebuild the dinosaur family tree using shared anatomical traits, not just overall similarity, but dozens or even hundreds of tiny details in bones and joints, each scored across many species. When we join these traits into a large data matrix and let a computer search for the simplest pattern of shared changes, we are not just drawing a tree. We are testing which arrangement of relationships best explains the distribution of features across the ancient world of dinosaurs. Even a single bone can sometimes speak this language. A massive sauropod vertebra might preserve the shape of its neural spine, the pattern of air-filled cavities, the angle of its articulating surfaces. A solitary theropod hip or femur might record the form of muscle scars, the depth of a groove, the twist of a shaft. Each of these becomes a character in the matrix, a yes or no, a present or absent, that lets the one-bone taxon be compared directly with better-known giants. When we run the analysis, the software produces evolutionary trees that show where that fragment fits best. Does it consistently group with titanosaurs from South America? Does it nest among Jurassic diplodocids? Or does it drift? If the supposed species jumps from one major branch to another with only the slightest change in assumptions, that instability is a warning sign. It means the available characters do not anchor it securely anywhere on the tree. In technical terms, these unstable taxa are called wildcards, but the implication is simple. If a bone can be equally at home with several very different dinosaur groups, then it probably does not preserve enough unique information to justify a separate name. Many legendary giants proposed from single vertebrae or limb fragments fade under this scrutiny. When their characters are added to broad sauropod datasets, they refuse to settle, and their claim to being distinct species, let alone the biggest creatures to ever walk the earth, begins to crumble. This does not make the fossils worthless. They still tell us that large animals lived in that time and place, and they still help set the stage for size estimates and biomechanical models. But as phylogenetic methods grow more comprehensive, they expose which names rest on solid evolutionary signal and which rest on wishful thinking. In the next section, we will see how this shifting of fragments on the tree reshapes our records of maximum size, and why a single reinterpreted bone can force us to rewrite the league tables of dinosaur gigantism. Those league tables do not just rank the biggest creatures to ever walk the earth, they also feed directly into how we count species, track biodiversity, and time waves of extinction and recovery. Every name on that list, even one built on a single battered vertebra, is treated as if it represents a real ecological player in an ancient ecosystem. When researchers reconstruct a Jurassic floodplain or a Cretaceous coastal plain on their computers, they rarely see just bones. They see herbivores filling different feeding heights, predators of different sizes, scavengers and specialists. Each named species becomes a data point in that web. It is counted in diversity curves, in graphs of who appears and who vanishes, and in models that estimate how crowded a habitat was. If a one-bone sauropod is logged as a distinct taxon, it can make a formation look unusually rich in giants, even if that fragment really belonged to a species we already know. This is where the hidden cost appears. In the 20th century, a flurry of fragmentary taxa, many based on single bones, seemed to swell dinosaur diversity. Names like Ultrasaurus or the lost giant Amphicoelius fragilimus briefly suggested sudden bursts of colossal sauropods in particular layers. For a time, those names were folded into diversity studies, creating apparent spikes in turnover, as if new lineages of giants were constantly rising and falling. But as those one-bone species were re-examined, several were quietly synonymized or declared dubious, and the spikes began to flatten. When we step back hundreds of millions of years using corrected datasets, a different picture emerges. Remove the poorly supported taxa, and what once looked like an explosive radiation of sauropods can resolve into a steadier, more gradual expansion. Apparent crashes in diversity, tied to the disappearance of a string of fragile names, can soften into slow declines. The overall pattern of evolution does not vanish, but its tempo changes. We move from a story of constant booms and busts to one of long rolling transitions across the Mesozoic era. This is why modern studies increasingly filter out one-bone and otherwise dubious species before they run the numbers. It feels conservative. It shrinks the cast list. Yet it also strips away noise created by repeat namings of the same animal, misidentified bones, and specimens that simply lack diagnostic features. The result is a leaner, more reliable curve of dinosaur history, one that still reveals massive radiations and real extinction events, but with fewer illusions. Join us as we follow this shift in practice, because it does more than tidy up charts. It begins to reset how we imagine entire worlds of scale we can barely imagine. If many of our supposed giants dissolve back into a handful of well-founded lineages, what does that do to our picture of sauropod dominance, of predator-prey balance, of the true upper limits of size? In the next section, we will see how recalibrating diversity does not just smooth graphs. It can overturn which periods we thought were the true golden ages of gigantism. When those graphs of diversity and size begin to flatten, something else dramatic happens. The skyline of supposed record breakers, those isolated spikes of nearly mythical proportions, starts to sink back toward the horizon. Not because the ancient world was small, but because our evidence for some of its most colossal residents turns out to be far thinner than we once hoped. Take Amphicoelius fragilimus, now often called Mara Apunisaurus. For decades, a single sketch of a single vertebra, long since lost, set the stage for claims of a sauropod over 50 meters long, the biggest creature to ever walk the earth by a huge margin. Today, most researchers treat that estimate with deep caution. The bone may have been mismeasured, misinterpreted, or even misassigned. Without the fossil, we are left with a ghost in the record, not a firm data point. Ultrasauros suffered a similar fate. Once hailed as a supersauropod from the Jurassic of North America, it turned out to be a chimera, a mix of bones from Supersaurus and Brachiosaurus. The name has faded, and with it, one of the towering peaks on our size charts. Bryhathchaiosaurus, described from fragmentary and now reportedly destroyed bones in India, has slid from maybe the largest dinosaur ever into a cloud of uncertainty. Was it truly a titanosaur? Were the bones even dinosaurian? We may never know. When we peel away these dubious giants, the timeline of maximum size shifts. Instead of a scattered handful of nearly unimaginable monsters appearing in many periods, we see a more coherent story. Gigantism in sauropods seems to build through the late Jurassic, then reach its most reliable extremes in the late Cretaceous, especially in South America. The apparent spikes in earlier intervals often vanish once we remove names based on a single questionable vertebra or a fragment of hip. In their place stand animals like Argentinosaurus, Patagotitan, and Dreadnoughtus. They are still massive, still awe-inspiring, but they are anchored in multiple bones, partial skeletons, and cross-checked estimates. Their limb bones can be compared, their vertebrae measured, their body volumes modeled. These giants may be a few meters shorter than the most extravagant one-bone legends, yet they give us trustworthy benchmarks for what life on Earth actually achieved. This raises a deeper question. Should we celebrate the possible extremes hinted at by fragile, ambiguous fossils? Or should we restrict our picture of dinosaur limits to what the rock record can firmly support? If we choose the first path, we embrace a world of scale we can barely imagine, but we risk building castles on sand. If we choose the second, we may understate the true ceiling of dinosaur size. Yet our reconstructions stand on solid ground. Join us as we carry this tension forward, because it shapes how we model ecosystems, climates, and even extinction. In the next section, we will ask, if the firm upper limit is set by Argentinosaurus-sized titans, what does that reveal about the physics and biology that governed how big giants could become? But before we can understand the physics of the very largest giants, we have to face a quieter problem. Our list of dinosaur species itself is unstable. On paper, the ancient world looks crowded with names. In reality, many of those names rest on a single fragile bone. To fix this, paleontologists undertake comprehensive taxonomic revisions. These are slow, meticulous audits of the fossil record. Experts return to the original descriptions, reread 19th century papers, and track down the actual bones in museum drawers. They compare those type specimens, the single fossil that legally defines each species, to better, more complete skeletons from the same formation and period. They ask, does this bone really show unique anatomy, or could it belong to a dinosaur we already know? When we join these researchers in the collections, we see how systematic this work has become. Measurements are repeated, surfaces are examined under new lighting, and CT scans reveal internal structure. Historical context is reconstructed. Who collected the fossil, from exactly which rock layer, and what other species were found nearby? In effect, scientists step back hundreds of millions of years and then work forward again, rebuilding the story around each name. Major review projects have already reshaped the catalog of the biggest creatures to ever walk the Earth. Revisions of Morrison Formation sauropods in North America, for example, have trimmed a thicket of names down to a smaller set of robust species such as Diplodocus, Apatosaurus, and Camarasaurus. Similar cleanups in Cretaceous South America and Asia have reduced long lists of titanosaurs, showing that some supposed diversity was an illusion built from scattered ribs, vertebrae, and limb fragments. At the heart of every decision is the type specimen. If that defining bone preserves clear diagnostic features, particular shapes of joints, processes, or ridges that cannot be confused, then the species may stand. If it overlaps completely with a better-known dinosaur, the name can be merged as a junior synonym. And if the bone is too worn, too incomplete, or too generic to distinguish at all, the species is often declared a nomen dubium, a dubious name that should no longer be used. How many one-bone giants vanish when judged by that standard? This cleanup does not stay hidden in technical journals. Museum labels are rewritten as names are merged or discarded. Popular dinosaur books quietly drop once famous colossi or move them to sidebars marked dubious. Online databases that many of us consult for size charts and family trees are updated, sometimes overnight, erasing record holders that once seemed secure. Join us as we recognize that every revision ripples outward, changing the way we picture ecosystems, evolution, and even extinction itself. In the next section, we will set the stage for a closer look at specific one-bone legends, species built on a single vertebra or limb, and ask what happens when those colossal claims meet the hard discipline of modern revision. Those one-bone legends sound dramatic, even romantic. But when should a single fragment be allowed to stand for an entire species of some of the biggest creatures to ever walk the earth? Modern vertebrate paleontology has become far stricter than the freewheeling days of the 19th century. Today, if we name a new taxon, we are expected to show that its type specimen has clear diagnostic features, shapes, proportions, or surface details that cannot reasonably belong to any already named dinosaur. That means meticulous description, high-resolution photographs, CT scans when possible, and exhaustive comparison with known material from the same period and region. A single vertebra is not enough by itself. It must carry unique information, set apart within the colossal family tree of dinosaur evolution. This is where excitement collides with responsibility. Discovering a strange bone in an ancient rock layer is thrilling. The temptation is to give it a new name, to carve a fresh chapter into the story of the Mesozoic era. Yet every name added to the literature is a permanent piece of scientific infrastructure. If the diagnosis is weak, later researchers must spend decades untangling synonyms, nomina dubia, and misidentifications. The cost is not just confusion, it is a distorted picture of diversity, of how many giants truly walked the earth, and how their rise and extinction unfolded. Some paleontologists argue for extreme caution. In their view, if a bone cannot be shown to be uniquely different, it should be left unnamed or assigned conservatively to a broader group. Why risk building castles on sand? They point to cases where supposed record holders, known from only one or two bones, have vanished into doubt once better fossils emerged. To them, restraint protects us from inflating the number of species and from chasing phantom giants. Others see value in a bolder approach. For these researchers, a carefully argued name, even for a fragment, is a hypothesis to be tested. If a distinctive tail vertebra or hip fragment really does not match anything known, giving it a name can focus future work. It flags a potential lineage, a clue that something massive and unexpected once lived in that ecosystem. They accept that some names will later fall, but regard that pruning as a normal part of scientific evolution. Journals, peer reviewers, and the formal codes of zoological nomenclature now stand between those impulses. Reviewers demand stronger evidence, clearer comparisons, and explicit statements of what exactly makes a one-bone species unique. Some journals discourage naming based on extremely fragmentary remains, unless the material is truly extraordinary. At the same time, the rules still allow such names when justified, trying not to silence genuine discoveries hiding in the rocks. So, where is the line, and who decides when a single bone is enough? In the next section, we will step back hundreds of millions of years to meet specific case studies, named from lone vertebrae and isolated limbs, and watch how modern scrutiny can either uphold those titans or quietly erase them from the roster of giants. Join us as we follow those fragile claims into a world of scale we can barely imagine. But while scientists quietly retire some of these fragile names, the public story of dinosaurs often keeps marching on unchanged. Once a dinosaur enters the imagination, it can linger there for decades, even if its scientific foundation has crumbled to dust. In books, games, and documentaries, the roster of giants can look far more crowded than the carefully pruned lists researchers actually trust. This split is especially sharp for one-bone and fragmentary species. A name like Ultrasauros, born from a few massive bones in Colorado, still appears in children's encyclopedias and trading cards as one of the biggest creatures to ever walk the earth. Yet the scientific verdict has shifted. Those bones are now understood to belong mostly to Supersaurus and Brachiosaurus, making Ultrasauros a duplicate, not a distinct titan. Amphicoelius fragilis, once promoted as an almost unimaginable colossus, survives in popular media as a record breaker, even though its defining vertebra is lost and its measurements are questioned. We see the same pattern with Bruhathcaiosaurus, a name attached to fragmentary remains from India that may not even be dinosaurian. Articles and online videos still repeat its supposed size, sketching silhouettes that dwarf Argentinosaurus, while specialists debate whether the original fossils were misidentified or too damaged to trust. When we step back hundreds of millions of years in our imagination, these names feel solid, like real animals walking through an ancient world. In the technical literature, many of them are closer to question marks. Museums stand directly at this crossroads between stable science and enduring myth. Curators must decide when to change a label, when to retire a familiar name, and when to leave it in place with added explanation. Renaming a skeleton from Ultrasauros to Supersaurus is not just a matter of swapping text. It means redesigning panels, reprinting guides, retraining staff, and sometimes disappointing visitors who came to see a specific celebrity. How often can a Hall of Giants be rewritten before it feels unstable to the public? Yet uncertainty does not have to diminish wonder. It can deepen it. When a museum label explains that a colossal femur once hailed as a new species is now thought to belong to an already known sauropod, it invites you into the process of discovery rather than only its end result. When a documentary pauses to say, "This name is debated, this size estimate is provisional," it reveals that our picture of dinosaur evolution is alive, not frozen. Join us as we imagine galleries where one-bone species are presented as mysteries in progress, their silhouettes outlined, but not filled in. What happens when we let the questions stand beside the giants themselves? And what does that reveal about the next fossil that might overturn the story again? Those questions do more than decorate the exhibit. They admit a hard truth about the ancient world. Our view of deep time will always be incomplete. Before humans, before cities, before history itself, vast lineages of giants rose and vanished, leaving behind only scattered traces. Most of the dinosaurs that walked the earth will never be known to us at all. Of those that are, many will be forever reduced to scraps. This is not a temporary problem. It is the condition of paleontology. Bones rot, sediments erode, whole ecosystems are ground down by plate tectonics and ice. When we step back hundreds of millions of years, we are lucky to find a single vertebra from a colossal sauropod or a fragment of jaw from a predator that once stalked a world of scale we can barely imagine. One bone or a handful of bones may be all we ever see of an entire evolutionary experiment. So how do we work with that? By treating names as hypotheses, not monuments. A species named from one rib or one-tail vertebra is not a final verdict. It is a carefully framed guess that can be tested as new material appears. When later fossils show that a supposed record breaker overlaps perfectly with a known dinosaur, that name can be folded into its older relative or set aside as doubtful. The system is self-correcting precisely because it allows us to say, "maybe," out loud. In this way, even the most fragile fragmentary taxa help science move forward. They mark possibilities. They tell other researchers, something like this existed here, in this layer, at this time. A single sauropod limb bone, even without a firm species identity, can still reveal body size through scaling relationships, hinting that massive herbivores roamed a region earlier than we thought. A lonely tooth in marine sediments can extend a group's range by millions of years or thousands of kilometers, reshaping maps of ancient geography and migration. Join us as we follow those clues across continents and through stacked layers of rock. Each scrap, named or unnamed, helps set the stage for broader stories. Where giant lineages originated, how they responded to climate shifts, which branches flourished, and which faded long before the final extinction. Without these maybes, the Mesozoic era would collapse into a handful of famous skeletons, and the true diversity of the biggest creatures to ever walk the earth would be lost. Yet the story does not end with isolated bones and cautious labels. What happens when new digs uncover skeletons that match these mysterious fragments, or when CT scans and 3D models pull hidden details from rock-bound fossils? In the next chapter, we explore how future discoveries in emerging technologies may finally give faces, bodies, and even behaviors to these one-bone ghosts, and how that might overturn our sense of dinosaur size and power all over again. But as we peer into that future, we also have to look back and admit something uncomfortable. Our record books for dinosaur size and diversity have never been fixed tablets of stone. They have shifted, sometimes dramatically, as the most fragmentary one-bone species are questioned, remeasured, or quietly moved to the margins. For more than a century, charts of biggest ever dinosaurs have been built on a few colossal ghosts. Names like Amphicoelias fragilis, now often called Mara apunisaurus, or the mysterious Bruhathkaiosaurus, were once presented as the biggest creatures to ever walk the earth. Their estimated lengths stretched far beyond Argentinosaurus or Patagotitan into a world of scale we can barely imagine. Yet when we look closely, what are these giants standing on? In some cases, a single vertebra, a fragment of hip, a bone that was described in the 1870s and then lost, never photographed clearly, never scanned. When modern paleontologists revisit these claims, the results can be dramatic. A species might be downgraded from record breaker to indeterminate titanosaur. It might be folded into a better-known neighbor as a synonym, or declared a nomen dubium, a dubious name that can no longer be tied securely to any one dinosaur. On a diversity graph, that means a line vanishes. On a body size chart, a towering bar suddenly shrinks or fades. Imagine that chart for a moment. Along the horizontal axis, time flows from the Triassic to the end Cretaceous extinction. On the vertical axis, maximum body size climbs and dips. At first, a few immense spikes loom above the rest, representing those legendary, poorly known giants. Then we apply stricter standards. Only species backed by multiple bones, by overlapping material, by repeatable measurements. One by one, some of those spikes dim, retreating back into the main cluster of sauropods. What remains is still massive, but it is also more coherent. This is not a failure of paleontology. This is how science advances. Early in any field, bold claims and limited data set the stage for future work. As new fossils are found and new methods emerge, we test those claims. We keep what survives contact with reality and let the rest go. Join us as we watch that self-correction in action. When dubious one-bone taxa are stripped away, patterns in the Mesozoic become clearer. There are fewer impossible outliers and more believable trends. A steady rise of sauropod size in the Jurassic, regional peaks in the Cretaceous, biogeographic stories that actually match shifting continents and climates. The ancient world starts to look less chaotic and more like a system shaped by evolution, ecology, and deep time. Of course, there is an emotional cost. Many of us grew up with a favorite, biggest dinosaur that may now be demoted or erased. Is it disappointing to learn that a childhood titan rested on one fragile, lost bone? Yes, but we can reframe that loss as part of an ongoing investigation. The mystery does not vanish, it deepens. Which real, well-supported giant will take that vacant crown? Today, colossal sauropods such as Argentinosaurus, Patagotitan, and Dreadnoughtus, anchored by multiple vertebrae, limb bones, and sometimes partial skeletons, define the upper limits of dinosaur size far more securely than legendary names based on scraps. They form the solid pillars around which we reconstruct a world of giants. In this way, the fossil record is not a static scoreboard. It is a living document, constantly edited as one bone species are tested, confirmed, merged, or retired. And as we step back hundreds of millions of years, our picture of the biggest dinosaurs on Earth changes with it. Those edits are not just about tidying up names. They reshape the way we read deep time itself. Every dinosaur species we recognize, from a nearly complete skeleton to a lonely vertebra, becomes a data point in much larger stories. When scientists map where fossils are found, they are not only plotting dots on a globe. They are tracing ancient coastlines, vanished inland seas, and migration routes across splitting continents. When they chart first and last appearances, they are tracking how giants rose, flourished, and fell as climates warmed, cooled, and tipped toward extinction. In that framework, a single misidentified bone can cast a long shadow. If a fragmentary femur is declared a new species of colossal predator, it suddenly tells us that a particular region hosted its own unique hunter. Diversity curves rise. Regional maps light up with what appears to be an endemic fauna. To a viewer, those sweeping animations of the biggest creatures to ever walk the Earth look authoritative. But what if the foundation is wrong? Imagine this scenario. A massive femur emerges from a poorly dated Cretaceous layer on a southern continent. It is isolated, weathered, and missing its ends, but it looks slightly different from known theropods. A new name is coined. Decades later, that name appears in a major study arguing that this continent supported a distinct ecosystem of huge, homegrown predators, separate from northern lineages. The lone bone helps set the stage for claims of unique evolution under local climates. Then, more complete fossils are discovered. Careful comparison shows that the new predator is simply a large individual of a widespread genus already known from other continents. The supposed endemic giant vanishes into synonymy. Overnight, the map changes. What looked like a sharp biogeographic boundary softens into a continuous range. A dramatic story of isolation becomes a story of connection. Multiply that by dozens of one-bone taxa, and you can see the hidden cost. Phantom species inflate local diversity, making some intervals look like explosive radiations when they may be quiet plateaus. They can exaggerate extinction rates by appearing and disappearing in narrow slices of time. They can create illusory migration events as names hop between continents that the real animals never reached. In sparse data sets, where every taxon carries massive statistical weight, one mistaken label can bend entire curves of evolution. Paleontologists describe this as a struggle between signal and noise in the fossil record. The true signal is the underlying pattern of dinosaur evolution through the Mesozoic era. The rise of titanosaurs, the spread of ceratopsians, the final Cretaceous decline. Noise is everything that blurs that pattern. Misidentifications, undated layers, and over-eager species based on scraps. One-bone taxa sit right on that boundary. Treated cautiously, they can hint at hidden diversity. Treated uncritically, they drown real trends beneath statistical static. This is why stratigraphy and precise dating matter so deeply. When a bone can be tied to a well-constrained horizon, anchored by volcanic ash, magnetic reversals, or fossil pollen, it occupies a narrow, reliable slice of time. diversity spikes become easier to test. Apparent gaps shrink or sharpen. We no longer have to guess whether two lonely bones, separated by a hillside, are separated by thousands or millions of years. In response, many modern studies take a conservative approach. Dubious one-bone species are lumped into broader groups: large titanosaur, indeterminate abelisaurid, or excluded from certain analyses altogether. At first glance, this makes the ancient world look simpler and less crowded. Fewer names, fewer colored lines on evolutionary trees, fewer species marching across those animated maps. Yet what remains is far more trustworthy. The rise of titanosaurs across Gondwana, the expansion of ceratopsians through late Cretaceous North America, the staggered pattern of extinctions at the very end of the period, these patterns stand on firmer ground when noisy names are set aside. We trade some of the apparent richness for clarity about the giants that truly shaped their ecosystems. So the next time we watch a documentary sweep continents with migrating herds and stalking predators, it is worth asking, which of those names rest on complete skeletons and which rest on a single weathered bone? Behind every arrow on those maps lies a debate about which fossils deserve to speak for an entire species. Join us as we look more closely at how paleontologists decide when a lonely bone earns that voice and when it should remain an unnamed fragment of a much larger story. Those debates are not happening in a vacuum. They unfold inside a surprisingly strict system whose only job is to keep the names of these giants from sliding into chaos. Before a new dinosaur can stride into the scientific record, it has to pass through a framework of rules that might seem invisible to us, but quietly shape every species list and museum label we see. At the center of this framework is the International Code of Zoological Nomenclature, the ICZN. It does not decide which hypothesis about dinosaur evolution is correct, or which size estimate wins. Instead, it sets the stage for order. It defines what counts as a properly published name, what a type specimen is, and which name has priority when two labels collide. In a world where a single vertebra can define a species, these rules are the scaffolding that keeps the structure from collapsing. Under the code, every species must have a holotype, the particular specimen that legally anchors the name. Sometimes that is a nearly complete skeleton, sometimes it is one worn tailbone, but a name alone is not enough. Today, peer review demands detailed descriptions, measurements, and comparisons before a one-bone species can be accepted. Editors, reviewers, and museum curators act as gatekeepers, asking, is this fragment really distinct? Or is it just another piece of an already known dinosaur? In major museums, type specimen repositories function like vaults for deep time's most important pages. The original bones of Diplodocus, Tyrannosaurus, and many more obscure fossils are preserved, cataloged, and climate-controlled. Researchers from around the world can request access, travel to these collections, and examine the very bone that defines a name. This careful curation guards against loss, mislabeling, and the quiet erosion that once turned some colossal vertebrae into dust. Join us as we follow scientists back to those shelves. Teams now CT scan century-old type bones, revealing internal structures without damaging them. They compare them with new discoveries from Patagonia, Mongolia, or North Africa, slotting each fragment into shared digital datasets. Three-dimensional models, online databases, and global phylogenetic matrices allow many eyes to interrogate the same elusive fossil, often overturning earlier claims about size, identity, or even whether a specimen belongs to the biggest creatures to ever walk the earth. These revisions are rarely solitary. They are collaborative and sometimes contentious. One group may argue that a one-bone species is unique. Another may show it overlaps completely with a better-known dinosaur, reducing it to a junior synonym or declaring it a nomen dubium, a dubious name. When such conflicts threaten stability, researchers can even petition the ICZN to conserve a widely used name or suppress an older, confusing one. The system can bend slightly to preserve a coherent map of the ancient world. In this way, paleontologists become guardians of Deep Time's library, constantly checking and rechecking the catalog so that each name, from famous predators to obscure fragments, points to something as real and reliable as the fossil record allows. And yet, even with all these safeguards, what happens when the only copy of a record-breaking dinosaur has vanished, leaving behind nothing but a drawing and a claim of impossible size? In a way, those missing bones and vanished giants are not dead ends at all. They are cliffhangers. Each one-bone dinosaur is a story paused mid-chapter, waiting for the next page to be uncovered in rock that has not seen daylight for more than 100 million years. Out in the field, paleontologists treat these mysteries as treasure maps. They return to the same formations, the same hillsides and quarries, where an isolated vertebra or limb once emerged, because the rock that yielded one fragment may still cradle the rest of the skeleton. Layer by layer, season after season, they widen the search, tracing the exact horizons and ancient river channels that first set the stage for discovery. Today, that search is far from blind. High-resolution satellite imagery, drone mapping, and even laser-based remote sensing allow teams to scan entire landscapes before a single boot touches the ground. Subtle color changes in exposed cliffs, patterns of erosion, or the way a slope sheds debris can reveal fossil-rich bands of rock. Join us as we follow these surveys across deserts and badlands, where a promising outcrop might hold the missing ribs, hips, or skull that finally match an enigmatic bone named decades ago. Even the fossils we already have are not frozen in their scientific value. New preparation techniques, from micro-sandblasting to CT scanning, peel back layers of rock and reveal hidden anatomy. Fine muscle scars on a femur, delicate air sacs in a vertebra, or growth rings locked inside a limb can suddenly appear. Details that were invisible when some of these one-bone species were first described. With each new glimpse, we refine how these fragments compare to more complete giants. Geochemical tools add another dimension. Isotopic signatures in a single bone can tie it to specific environments, from coastal floodplains to upland forests, and to particular faunal assemblages living in that time and place. If an isolated sauropod vertebra shares the same age, chemistry, and sediment as a well-known species, does that pull it into an existing lineage or hint at a closely related but distinct titan? Every time a more complete skeleton emerges from a familiar formation, the questions sharpen. Does this new giant, perhaps stretching longer than a city bus, correspond to one of our named but fragmentary dinosaurs? Or does it represent an entirely new branch of evolution? Some legendary colossi, known only from a single vertebra or limb, may one day be vindicated by a near-complete skeleton that finally reveals their true proportions. Others will quietly fade, their names absorbed into older, better documented species, as we realize they were never unique at all. The Mesozoic era is still partly unexplored territory, a world of scale we can barely imagine. Each field season, each new scan, each unexpected bone weathering from an ancient hillside offers another chance to solve or deepen the mysteries left by those lonely fragments. But what happens when the next discovery does not just revise a single species, but reshapes our entire picture of how the biggest creatures to ever walk the earth lived and grew? When we picture that Jurassic Valley or Cretaceous floodplain, we see motion everywhere. Herds of sauropod giants, packs of predators, flocks of small feathered forms weaving between them. Yet every creature in that mental scene is anchored in the end to real fossils on real slabs of rock, sometimes to a beautiful skeleton, and sometimes to a single, lonely bone. This is where the one-bone problem reaches out of the museum drawer and reshapes the ancient world in our heads. If each fragmentary vertebra or hip is named as a brand new species, our reconstructed ecosystems begin to swell. Oversplitting from scraps, can make a single formation look overcrowded, as if dozens of nearly identical carnivores stalked the same riverbank, or as if 8 colossal sauropods with almost the same body plan all browsed the same stands of conifers. It feels dramatic. But is it real? A more conservative approach paints a different, cleaner picture. Instead of a chaotic crowd of names, we see fewer, better supported species stretching across wider ranges and broader ecological roles. One robust sauropod species might cover several feeding heights and habitats through age differences within the herd, rather than 3 nearly indistinguishable species doing the same job. The landscape is still vibrant, still a world of scale we can barely imagine, but the cast list is shorter and clearer. This matters because our food webs are only as reliable as the species we feed into them. Predator-prey ratios, ideas about niche partitioning, even estimates of how much vegetation a region could support, all depend on how many valid dinosaurs we recognize from a given place and time. Do we see a top-heavy ecosystem teetering under too many massive hunters, or a more balanced community where a few apex predators shadow vast herds of herbivores? Join us as we step back hundreds of millions of years to a late Jurassic floodplain. Here, the difference between 3 giant sauropod species and 8 is enormous. With 3, we might imagine broad migration routes, mixed-age herds sweeping across open country, and forests recovering between seasonal feeding waves. With 8, we are forced to picture near-constant pressure on vegetation, intense competition at every waterhole, and a patchwork of tiny, tightly packed niches. The rock layers themselves have not changed, only our taxonomic choices have. Those choices also ripple into art and film. A single enormous vertebra, tentatively named, can tempt us to populate documentaries with spectacular but poorly supported creatures, towering over the biggest creatures to ever walk the earth that we actually know well. One-bone taxa can quietly inflate the drama on screen, while leaving audiences with the impression that these animals are as solid as a nearly complete skeleton. Responsible paleoart now tries to meet this challenge head-on. Many artists and filmmakers focus on well-supported species, or clearly flag uncertain forms as hypothetical, while still letting fragmentary finds hint at shapes moving just beyond the firelight of evidence. Accepting uncertainty does not make the dinosaur world smaller. It makes it deeper, layered with multiple plausible versions of each ecosystem, each one a testable story about evolution, survival, and extinction on an ancient Earth. In the end, our picture of dinosaur life is a carefully balanced blend of hardbone and informed inference. How we treat species known from a single bone can tilt that balance toward clarity or confusion. And in the next section, we will see how new discoveries can suddenly push it one way or the other. That balance between hard bone and informed inference is exactly where you and I enter the story. When a headline declares the biggest dinosaur ever, or a terrifying new predator, we feel the pull of a world of scale we can barely imagine. But behind many of those dramatic claims, there may be only a single vertebra, a fragment of hip, or a lonely limb bone. So how do we, as viewers, read those stories like scientists rather than just spectators? The first question is simple. How complete is the specimen? Not just a fossil was found, but which bones and how many? Is it a partial skeleton with skull, limbs, and vertebrae? Or is the entire colossal animal hanging on one bone the size of a suitcase? When you see that spelled out, the strength of the claim becomes much clearer. Next, look for the type specimen. Every named species is anchored to a particular fossil, the holotype, that legally defines its name. Is that clearly identified with a museum number and a description? Or is the article vague about what actually carries the name? When we know which physical object sets the stage for the species, we can better judge how secure that name really is. Then ask whether the authors compared that bone rigorously to similar known species. Do they show how their giant differs from Argentinosaurus or Patagotitan, or from other predators of the same era and region? Or does the story leap straight from unusual bone to new record-breaking giant without walking us through the anatomy? Careful comparison is the backbone of trustworthy claims. Pay attention to time and place. Does the report name a specific rock formation and geological age, or just say late in the dinosaur era? Knowing whether a bone comes from the Morrison Formation or Cretaceous coastal plain helps us fit it into the broader evolution of the biggest creatures to ever walk the earth. If you ever glance at the original paper, the language itself is a guide. Terms like CF, compare with, AFF, affinity with, or indeterminate sauropod may sound cautious, but that caution is healthy. It tells us the scientists are resisting the temptation to turn one ambiguous fragment into a fully formed giant, even if the media coverage sounds far more certain. Another question: do other experts weigh in? Responsible coverage will mention if some paleontologists doubt the size estimate or think the bone might belong to a known species. Debate does not weaken the science. It is the process by which our picture of ancient Earth sharpens over time. To move beyond the headline, we can follow up with museum blogs, reputable science news outlets, or even just the abstract of the original paper. Join us as we trace a claim back to its source, and we begin to see not just a monster in the mist, but the actual evidence on which that monster rests. When we ask these questions, we are not being cynical. We are helping science remain self-correcting, keeping our stories of giants anchored to reality. In the end, each new one-bone dinosaur is not just a creature, but a hypothesis, waiting for future fossils, and perhaps your own curiosity, to test it further. And somewhere out there, that hypothesis is still buried in stone. Picture it one last time: a solitary vertebra, half buried in pale sandstone, its curve just breaking the surface after a rainstorm. Or a colossal femur, emerging from a cliff face like the pillar of a ruined temple. For more than a century, we have built vast portions of our dinosaur story on discoveries exactly like this, on single bones that seem to whisper of giants and a world of scale we can barely imagine. In this episode, we have followed that whisper from its first echo to its latest revision. We have watched paleontologists in the early days seize on lone bones to name new species, sometimes even proclaiming the biggest creatures to ever walk the earth from a single vertebra or limb. We have stepped into the taxonomic tangles that followed: wastebasket genera, duplicate names, and fossils like Amphicoelias fragilis, Bruhathchiosaurus, and Ultrasauros that blurred the line between data and legend. Then we watched modern tools: CT scanners, 3D models, careful stratigraphy, and rigorous evolutionary trees test those claims, rescuing a few and overturning many. What emerges is a powerful paradox. A single fossil can illuminate. It anchors a moment in deep time, tells us that in this place, in this layer, a particular kind of dinosaur truly lived. Yet that same bone can mislead, tempting us to see a complete animal where there is only a fragment, to draw hard boundaries around a species that might never have existed as we imagine it. How much certainty can we really claim when everything rests on one fragile piece of ancient bone? The answer is not to stop naming or to abandon bold ideas. Instead, it is to pair every bold hypothesis with humility. Each one-bone dinosaur should be treated as a question mark carved in rock, an invitation to keep digging, to keep comparing, to keep refining. When later fossils show that a supposed titan was just a familiar sauropod seen from a strange angle, that correction is not a failure. It is the scientific process doing exactly what it is meant to do. Names may change. Colossal giants may shrink to more modest sizes. Some species may fade into synonymy and become footnotes in the history of this field. But with every revision, our picture of dinosaur evolution, diversity, and ecology grows sharper. We trade a few broken myths for a clear view of the real ancient world that once covered this earth. And at the heart of that world were living animals. Even the most fragmentary bone belonged to a creature that breathed, fed, and walked under alien constellations on a very familiar planet. When you stand in front of a lonely vertebra in a museum case, you are only a few meters away from a life that ended more than 100 million years ago. That distance is immense. Yet it is also close enough to touch. This is where you come in. By visiting museums, supporting fieldwork, following paleontology research, and encouraging the next generation of scientists, you help ensure that today's mysteries do not remain mysteries forever. Somewhere, in rocks that no human hand has yet brushed clean, lie the rest of those skeletons. The missing necks and hips and skulls that will confirm legends, topple records, and reveal dinosaurs we have not yet imagined. Join us as we continue to step back hundreds of millions of years, one bone at a time, listening for new stories in the stone, because as long as even a single fossil remains hidden in the ground, the age of discovery is not over. It is only just beginning.